Let's talk about some particles. We have just finished uploading the entire material course. If you haven't seen that one yet, I do recommend you go check that out first, because if you're going to be making particle systems, particles interact with particle materials. And for that, you're going to need to have at least a basic understanding of how to set up your materials. We're going to go over the particle-specific stuff in this series, so don't worry about that. But you probably should understand a little bit about like material math and UV math and that kind of thing. But without further ado, let's get into it. We're going to go ahead and make ourselves some particles. So here under effects, we have the Niagara emitter and the Niagara system, and then we've got some advanced stuff that we're not gonna worry about. This is a introductory series. And what is the difference between these two, right? When do I make a system and when do I make an emitter? Well, that's actually quite easy. Niagara systems are the thing that you physically place in the world, and Niagara emitters are parts of those systems. So if we make a Niagara system here, we can choose between a whole bunch of pre-existing emitters. A lot of this comes with the learning content, so a lot of this actually shows you how particle systems work. So if I don't cover something very well, you can go in and check out these learning materials as well. And if I, for instance, do this kill particles, and I open up this system, you will see that it has this entire system with a couple of notes explaining how things work. So that is quite nice, because I am unlikely to cover literally everything that you could ever possibly know about particles. So that's a good secondary source of information. Now that we have this one open here anyway, actually, let's talk about emitters, because this thing over here is an emitter. And what does that actually mean? Well, a system can have multiple emitters. So we chose the kill particles emitter when we set up this system, but we can add another one if we want to. So we can say, I also want the infinite particle lifetime, which is just going to be one particle that infinitely exists, more or less. And that will then coexist inside of this system with the kill particle. And the kill particles just bugged out a little bit there. So both of these emitters together, the kill particles are acting up a little bit weirdly, will make this system. And that is the basic rundown of how this works, is you add multiple of these emitters together to make a system, and then you put the system into the world. As a matter of fact, if we make our own emitter, which let's just do that real quick, you can go into effects and just make an Niagara emitter, and then you can choose one of these emitters to just kind of copy everything off of and then change things to your liking. So quite often I will end up using the, it's not in the learning content, it's in the template. The fountain, for instance, is a very common one that I will end up using, or the omnidirectional burst. Let's do the omnidirectional burst, right? So this will be burst FX1, something like that. And when we open it up, it will have the default omnidirectional burst, which if we can get our camera close to it at some point, like right here, there we go. You can see it is a burst of particles that goes to all directions and has gravity. And you can see there's a bunch of stuff going on here. We'll talk all about that when we get to it. But for now, just know that we now have our own particle emitter. We can't put this emitter into the world. This is an emitter. This emitter can only go into a system, and then that system can go into the world. So let's open up our particle system again, and we can add another emitter. And the emitter that we just made, Burst FX1, is now one of the emitters that we can add. And the wonderful thing is, we can change things in here now, in our emitter, and it will immediately get updated in here as well. So if you have the same emitter in like 10 different particle systems, you have one place to just change it and everything is linked up together. But, and here we get into some really interesting stuff, you can still override things and add things to emitters in specific particle systems. So we have this burst FX1, right? And it does a bunch of stuff. But what if in this specific system we wanted to not have gravity? We can just disable the gravity in this system. The actual emitter itself, in all the other systems that it exists in, still has the gravity. It's just in this one, it doesn't now. So let's put this into the world, and it will like do a burst there, and it has the one singular particle that keeps spawning over and over and over again, and the kill particles still are being a little bit weird. So that is the relationship between systems and emitters. But then what is an emitter? How does an emitter build up? Because a system is built up out of different emitters. And an emitter here is built out of these singular modules. Every single one of these things is called a module. You can see as I go through them here, they all have their own settings and their own stuff going on, which you can make your own custom modules as well if you want to. That's a little bit more advanced. We're probably not going to be talking about that in this series. For the most part, with all the modules that pre-exist, like there's a lot of them. Like these are all categories, by the way. These are not just modules. Like these are, like, a lot of these have multiple different things inside of them. We're not going to cover all of these because learning all of these one by one out of any sort of context wouldn't be a productive use of my time in making these videos. It wouldn't be a productive use of your time in learning Niagara. Suffice to say, we're going to make one more emitter here, and we'll make that out of an empty emitter. There's also a template that is called something like completely empty. I don't like using that one. If I just start from scratch, I use empty. Again, often I'll just piggyback off of the fountain or the omnidirectional burst, sometimes the hanging particles or directional burst. Those are the common ones that I use. Dynamic beam. We'll talk a little bit about beams and ribbons as well in the future. For now, let's just go with a empty particle system though. So let's call this empty one. And this is all that we will have when we make an empty particle emitter. So what do we have here, right? We've got emitter spawn. Everything that you put in here, all the modules, and each module you can see kind of as like a function, right? As a little bit of code that runs. So emitter spawn only runs once when the emitter is initially spawned. So if you need to set any values, generate any like random values or whatever that stay consistent throughout the entire lifetime of the emitter, that is where you do it. Then the emitter has its own update loop, which is effectively just a tick event that will allow you to, most of the time, just spawn in the particles. You also have this emitter state function, or module rather, already pre-built there for you. But for the most part, you're just going to be putting particle spawners in here. Then, just like the emitter has a spawn and an update, each individual particle also has their update and their spawn. So this will only run once for the emitter, effectively begin play, right? For the emitter, when the emitter is spawned in, this will run once. Particle spawn will run once for every particle that spawns in. So if we're spawning in like 10 particles, every single one of those is going to have its own particle spawn. So if you set a random value in emitter spawn, it's always going to be consistently the same until you spawn in another system which will have another random value. For particle spawn, every particle that's going to spawn, if you set a random value in here, is going to have its own random value. Particle update is just, again, more or less the event tick of your particle. So if your particle needs to change color over its lifetime, or it needs to change color based on its speed, or it needs to change its shape based on whatever, it needs to do something with the material based on, again, literally anything that you can imagine, that will all be going on in particle update, as well as things like applying forces. So moving your particle around, for the most part, will be done in particle update. All this just calculates stuff for a point. Nothing is being rendered yet. And that is where we get into the renderer. And this I'm actually going to show you right away, because the renderer does really only a couple of options. We've got a decal renderer, like a light renderer, a volume renderer, all that kind of stuff. For the most part, there's only 3 renderers that you often will use. For the most part, like by far the most common, will probably be the sprite renderer. It is a default renderer. This will render by default a sprite with a material. So that's just a little square with a material on it. And the default sprite material has something set up in it. a little bit of all this going on. We'll talk more about like this particle color node, for instance, a little bit later. And effectively what this does is it just creates it's a sphere mask, but you can see it's on a 2D plane. So it just creates a circle. So your default particle is just going to be a circle that you can set some information on. If for whatever reason you clear out this material and you want to get our like default sprite material back, you might not see it immediately. And if that happens, you want to click on the options here and you want to show plugin content. And maybe also show engine content. Yeah, you also need to have show engine content enabled. And then you'll be able to see our default sprite material. So we can put that back now. And we have our default sprite material again. But we can also, instead of rendering a sprite, what we can do is the most often used is the ribbon renderer as well as the mesh renderer. And the mesh renderer, you can obviously just render pretty much any 3D static mesh that you want as a particle, which is quite nice. We are not spawning in any particles at the moment yet though, and that is because this is just a brief overview of like the structure of how these systems are going to work. I think just having this as its own part to compartmentalize how this works is a good thing before we move forward with actually spawning in particles. So next time we're going to be filling in this empty emitter. We're going to put it into a system and we're going to have a particle spawn in and maybe it'll do some stuff. On our journey making particles, we have covered a lot of like theory last time. So let's put some of that into practice. Today we're going to be spawning in our first particles. As a little bit of a recap, we have like a system setup here and a burst effect setup. We're going to get rid of that. That was just to show you the structure of how everything works. But we also have this empty emitter 1, which is just an empty emitter. I put in a mesh renderer there. Let's stick with the normal sprite renderer because that's the default that we have. And we're going to go through step by step and spawn in a particle and do some basic stuff with it so that you can really start to appreciate how these modules work. So again, last time we went over what these categories mean. So we have like this emitter summary, but for the most part we have emitter spawn, emitter update, particle spawn and particle update. So in emitter spawn we effectively like don't really do anything for the moment. We can ignore that. Emitter update is where we put in our spawning stuff. So if we just click on that plus and we try to type in spawn, we see we have a couple of different options. We can spawn burst instantaneous, so that will allow us to spawn a certain amount of particles all at the same time. We can say spawn per unit. We're going to ignore that one for now because it's a little bit niche. But for instance, if you want to spawn a particle like every 100 units that a system moves, that is something you can use. And if you generally you would do that for ribbon particles, right? Because ribbon particles connect through like every particle that they spawn. We'll make a video specifically about ribbon particles. Don't worry about that. Spawn per unit will be useful for that. Or maybe in that video I will cover it. But for the most part, you don't use this too often. And then we've got spawn rate, which is exactly what it sounds like. It just spawns the amount of particles that you give it per second. So let's show off both of them. We have the spawn burst instantaneous. And if we set the spawn count to like 500, it'll spawn 500 particles here in the middle. And it won't really do anything else at the moment yet, because we don't have anything telling it to do something. It's as easy as that. So let's tell it to do something. And that is on particle spawn, we can tell it to do a thing. For instance, we can add velocity. And we have to, when we add velocity, and this is the nice thing about Niagara, some modules have dependencies. So when we add velocity to a particle, we also need to include solve forces and velocity, so that the particle system can calculate where everything needs to move and stuff. It just gives you these buttons here, which you can just click to fix any dependency issues that you might have. So we just fix issue and boom. Now we have a particle that moves upward when it spawns in. But it spawns all of them in at the same time and they all move exactly in the same direction. So it just seems like we still only have one. So maybe instead of all spawning them in the same place, what we want to do is we want to spawn in a shape location. This is another one that you're going to be using a lot. You can also spawn things on the surface, for instance, of a static mesh or even a skeletal mesh. I have a separate video about this, which is really, really cool. But a lot of the time you're going to spawn things in a shape location. And what that will do is, in this case, it'll by default say it spawns them in a sphere, and that sphere radius will be 100. So it'll kind of just calculate a sphere with a radius of 100, and every time it spawns a particle on it, it will spawn it at a random place on the surface of that sphere. At least that is the default behavior. You can spawn them randomly. You can spawn them what is called direct, which will give you the U and V positional data. So you can specifically say where on the sphere you want it to spawn. And if you spawn them uniform, it kind of does what it sounds like it will do, right? It spawns all of the particles from spawn burst instantaneous, evenly spread across the sphere. Of course, we have multiple different types of shapes that we have. We have a cylinder or a box / plane, a torus, which is a donut shape, which is quite nice for a lot of things as well. Then we've got a ring, which is a donut shape, but in 2D, so it doesn't have like actual height, it's just a ring. And then we've got the cone as well, which is just a cone shape. And there we have a spherical cone or a spherical wedge. That's all fine. Let's stick with the sphere. I do want to show you some differences though, because this is all with spawn burst instantaneous, which is quite nice. But what if we change this over to spawn rate instead? And we spawn, for instance, 15 particles per second. We still, in our shape location, have this thing set to uniform. But because it's only spawning one particle at a time, it's uniformly spawning that in the middle of the shape. So that doesn't actually work all that well with uniform. But unlike with spawn burst instantaneous, with direct was a little bit useless, because it was just, you needed to pass in the exact coordinates of where you want to spawn it, and it can be a little bit bothersome. If you use spawn rate, it will actually kind of spawn them across the surface of your sphere in order, which will create this very like neat circular effect, which is kind of nice. Specifically as well, if you do this on a ring instead, and you set this again to direct, it really starts creating this little spring shape, which is quite nice to be able to do. There's a lot of things that you can play around with here. You can have like the disk coverage in this case for the ring, so that's also like, does it spawn things on the surface or only on the outside? And then we have some distribution stuff. We're not going to really bother too much with that. For now, let's go back to the sphere, and let's do this just randomly. So we now have these spawning on a sphere and going into the sky at a velocity of 50 units upward. So we can also give them 50 units in the Y, and now they all move in that direction. And we can give them 50 units in the X, and now they move in all three directions in the positive, right? So this is just how that works. And the thing is, there's a lot to do here. I want to talk a little bit more about like more advanced setups for like creating values for these things in its own separate video. For now, suffice it to say that with this little arrow thing here, we can upgrade this velocity from just being a vector 3 value to being something that is a little bit more based on calculation. And this is also where we can add in randomness. Because remember, we're now on particle spawn, so every single particle is going to run whatever code we put in here. So in this case, for its velocity, for itself. So if we say we have a random vector, and we set that vector scale to 50, now every single particle is going to be set off at its own velocity in its own direction. And we suddenly have like this thing going on, which is quite fun. And in much the same way, we can give this like a color as well. And the color, very much the same thing. We can get a random range linear color, which will give us a minimum color, let's say blue, and a maximum color, let's say red. And now everything is going to be colored between that red and that blue. And because this is in particle spawn, once again, this will randomly generate something for each individual particle for its data. But what if we don't want to just set one color and be done with it? What if we want to do something a little bit more dynamic? So let's get rid of the color in the particle spawn, and let's actually move to the particle update. Because what we can do is we can actually set, instead of the color directly, we can scale the color. And if we scale a value, that means that we're going to be able to change this to RGB and alpha together. This will make a vector 4, and we can get a vector 4 from curve. So this will create a gradient that will fade out from, in this case, white to white and from opaque to transparent. I'm going to set this opacity to a value of 1, just so that you can see it a little bit better. And if we set this color to like purple or pink, you can see as they near the end of their lifetime, they slowly turn pink. And that is because our curve index, this value that we have right here, is set to the normalized age. So that means that when we are at the left-hand side here, this is a normalized age of 0. So that's the beginning of their lifetime. All the way to the right here, we have the normalized age of 1, which is the end of their lifetime. That is what the normalized bit in normalized age means. Their age, how far along they are in their lifetime, shown as a value between 0 and 1. We can put anything we want in here. We can do a not normalized age. So just their age in, I think it is at that point, measured in milliseconds, or maybe in seconds. And that way we can say during the first second of your lifetime, you do this. And after that, you just stick at the value of 1. You can do a lot of other interesting stuff with it. You can, say, put in the velocity here instead. So when something is standing still, it'll have a color value of 0. And when it's moving at its, whatever its max speed is, it will have a color of pink, and so on and so forth. So you can do a lot of very fun stuff. Now, this is called a curve for colors. It's a gradient, so that's maybe a little bit confusing. So let's do something a little bit different. And that is, instead of just scaling the color, which again is a little weird because it's called a curve, let's scale the sprite size. So we can scale the sprite size, or we can scale the mesh size. That depends on whether or not you're using a sprite renderer or a mesh renderer, or God forbid, within the same emitter, both. We are using a sprite, of course, so we're going to scale sprite size. And that gets you a more normal looking curve, right? So here we have on the y-axis, we have the scale of our sprite. And then on the x-axis, we have the normalized age. So this is exactly the wrong way around. They start very small and they end very big now. We've got a couple of different like presets here that we can very easily use. So let's, for instance, use this one as a preset. And you can see that right now they seem to have disappeared. And that is because they are being set to an incredibly small number. So we have this uniform curve scale, and that just takes this curve, which usually you make these curves of between values of 0 and 1, just have them be workable. But then if you want them to actually apply bigger values, you increase the curve's scale. So if we set that to 50, it will be much bigger. What is also important to note is that in order for this to work, we actually need to go into the initialized particle thing here. And an empty emitter will come with an initialized particle. And this is where we set up a couple of important things. So we should probably take a look into this anyway. Because in here we have the lifetime mode, which is direct set for the most part, that's good. And then the lifetime, which is how long the particle will live, the color mode, the position, all that kind of stuff. The thing that we care about right now is our sprite size, because that is set to unset. If we're trying to set that then within our modules later down the line, like with our scale sprite size, it's not going to do anything. So what we need to do is we need to set sprite mode to whatever we want it to be. So we have got uniform, random uniform, non-uniform, and random non-uniform. So if we set it to uniform, we just get a float value for its size. So if we set this back to 1, it's very small, but it's getting scaled up by a factor of like 50 in our sprite size. So let's set this to factor 5 instead and keep this at the default value of 10, which will make the particles roughly the same size that they were just a moment ago. And you can already see that this feels like there's something happening, right? This feels quite organic and quite nice to look at. Now, we also have got a random uniform, and this will give each individual particle, when it is initialized, a random size between a minimum and a maximum. So we can give like the minimum for 2, and then the maximum can be like 25, which means that we have very big differences in the sizes of these particles. And then when this sprite size gets scaled, it gets scaled based on what the initial size that was applied to it is. So this is just a like curve that says what percentage of its actual size it is. Its actual size is set in the initialized particle, and then the scale sprite size just says, okay, you are now at 0% of that size. You are now at like 90-something% of that sprite size. And then toward the end here, you are once again at 0% of that size. And we can change the scale of that curve again with this value down here. And that's pretty much how it works for everything, right? So we can set its initial color, for instance, as well. So its color mode is unset right now. You can make a color with the module that we just showed you. But you can also just set it directly in here, and that just gives you a color to directly set. And of course, you can also do a random in range or a random hue saturation value. You can do a lot of like interesting, fun stuff with this. Now, one thing that you will note is that I changed the color here to, let's do random in range to like blue and maybe, like, let's do yellow, something like that, right? And they still fade out into a pinkish color, and the yellow ones fade out into an orangish color, which is what, like, we never said orange anywhere. What the hell is happening there? That is because this scale color applies a tint to the base color. So if the base color is just white, this is just going to apply the color directly. But if the base color, for instance here, indeed is yellow, if this magenta gets applied to that yellow, that makes an orangish color. And of course we have, in the end, our sprite renderer, which has a bunch of other settings as well, which we'll eventually surely get into a little bit more. Feel free to explore that. I'm going to, just for laughs really, I'm going to add in a mesh renderer as well to show you. We can add in more than one mesh even if we want to, at which point I believe every single particle will take a random mesh out of this, or it will take all of them, or you can actually set up what you want to happen. So let's give it the like default cube here, like the static mesh shape cube. And it will spawn all of those in, which is like a very, very weird feeling thing. And you will notice that they don't actually scale up and down because we are setting the sprite size by curve, but we're not doing any such thing about the mesh size. So if we want to scale the mesh in the same way, what we need to do is we need to scale the mesh size, which makes it disappear. Because, of course, in our initialized particle, we need to set our mesh scale mode to, in this case, let's just go for like uniform and set it to 1. And now it will scale them to 1, 1, 1, because we don't have a curve set up yet. Of course, we can set up a like vector from curve, and now they will shrink over their lifetime. Now, one last thing that I want to do, just to make this look a little bit more interesting, we actually have a facing mode option here. Specifically for meshes, this is interesting, because by default, it will just kind of spawn them in world aligned, and that's kind of boring. So we've got, we can make them always face toward the camera, which specifically for these cubes kind of makes them just into squares, right? So I probably don't want to do that. But that is something that you can do. You can make them align to the camera plane. So you will note the difference being is if you look at the particles that move away, they still rotate themselves in 3 directions toward the exact position of the camera. If we go into the camera plane, they just rotate themselves in the one direction to look into the general direction of the camera, but not at its exact position. By far the most fun and useful though one is aligned to velocity. So they will now rotate themselves toward the velocity that they're traveling in, which makes for a much more interesting looking system. Except of course there's not a system, this is an emitter. We need to put it inside of the system to actually do something with it. We've gone over that in the last video. For now though, I think that we have spawned in our first particle. We can add our sprite renderer back into this as well. It'll look a little bit weird to have both of them. Every single particle now has a mesh and a sprite, which is fun, I guess. And we'll leave off there for right now. I think there's a little bit of experimentation that you can do with this now. This was a lot of just throwing things at you to make sure that you have a basic understanding of like what is possible, like what options exist, and how to put in these separate modules and work with them and how they interact with each other and where to look if something isn't working, that kind of thing. I think you have a pretty good base now to start experimenting. Next time, we're going to go in a little bit deeper again, and we're going to do some more fun stuff. So I'll see you back then. Now, we have this mess of a particle system. I'm going to turn off the sprite renderer because I actually quite like the mesh renderer that we have here. But it just kind of spawns in the particles and then nothing else really happens. Like they move in one direction until they die, which is nice, but quite limited. So today I want to talk about the difference between applying a velocity and applying a force. And really easily, the difference can be summed up between the spawn particle and the update particle. Because we're adding velocity on spawn, but that just adds it once. So when the particle spawns, it'll immediately have a velocity, so it won't start as a stationary thing. If we turn this off, everything just starts as a stationary particle, and that, well, has its own unique look, but maybe not great. But in particle update, we have things like a drag, which slows down the velocity of your particles. So you can see they will now start with a velocity, but slowly move down in their speed. So now that we have drag, we probably want to give them a little bit more velocity when they start off. So let's give them a velocity of like 150. And you can see that they start out and then they almost like stop moving in mid-air, because particle update is now applying a stopping force, a opposing force to whatever direction they're moving in every single update cycle. But that can also, of course, go the other way around. And that is where forces come in. We can add in a bunch of different forces. So instead of adding a velocity at the start, so let's just get rid of this altogether just to make a point, and get rid of drag for now as well, just to show it a little bit better. We can add a force. And there is a bunch of forces that we can add: acceleration force, a gravity force, a linear force, a point force. There's a bunch of forces. Again, we're not going to go over all of the different forces. This is not Star Wars. I'm just going to show you a couple of the most common ones. So, of course, we have the gravity force. If we add that, things will start falling because there's now gravity. It's literally as simple as that. There's not much more to it. Another one that will be commonly used is the point force. And this will apply a force, anything that is close to it, in a direction away from it. So usually that will be something like the point force will just be at the center, and everything that spawns will now be moving away from the center. But you can do some more interesting stuff with this. You could, for instance, say, instead of just setting our point force to the simulation position, you can do some more interesting stuff and set it a little bit above it, so that everything is getting pushed down from that single point. That requires a little bit more complex setup though, so we'll probably come back to that idea a little bit later, because it requires us to get rid of the simulation position and then add it to something else, and that's a little bit annoying. But we have this point force, so everything is getting pushed away from the center, but we also have the exact opposite. So we have a attraction force. Instead of normal forces which push, these ones pull. So we also have a point and a line attraction force. Let's do a point attraction force, and this does the exact opposite, right? So it pulls everything into the center. And here's where we get into some really, really fun shit, because we can set the attraction radius to be a little bit bigger, just to make sure. And then if we set this attraction strength to something much bigger, like 150 for instance, or maybe even like 1500. And then we enable our point force again. The particles are now both being pushed and pulled into this position, which makes this little back and forth looking system. So let's actually set the spawn rate to like 2 particles instead, so we can see the movement a little bit better. It makes us like almost bobbing back and forth kind of movement, which is quite nice. And all this is happening in particle updates, so every single frame it's solving for all of these different forces that we're applying. So this is happening on its own cycle. Particle spawn, we set velocity directly, and we can do a lot of stuff, right? Because we can apply forces in here as well. We have certain forces like the curl noise force, which is a like soft random force that we can use. We can apply like 1 instance of that force on spawn and then not apply it on update again. We can do that. I don't know why you would want to do that, but you can. Speaking of the curl noise force though, let's also show off what that does, because that is probably a force that you've seen a lot of people make like very impressive looking particle systems with, because it looks very pretty very easily. I'm going to get rid of the gravity force as well, and let's add in our curl noise force. This is frankly just kind of a cheat code to make things look good, if I'm being honest with you. So if we increase the strength here a little bit and we decrease the frequency ever so slightly, and I spawn in a boatload more particles, so let's spawn like 1500. You can see these are all moving in their own random direction, and this doesn't really do all that much yet, but let's change a lot of things. Let's initialize particle at a much longer lifetime so that we can actually see these things moving around. And you will start seeing at some point that this forms a certain almost wave-like pattern. If we increase the strength a little bit more, even to like 200, and we increase a little bit of drag, so the drag will also kind of keep these particles in groupings. So if you play around a little bit with some values there, so I increased the noise strength to quite a large number and then decreased the frequency to like quite a low number here. This really shows off what it does very well with the particles facing in the direction that they have velocity, because you can see them kind of wiggling around because they're following a noise path. And that creates this quite pleasant looking movement that feels kind of like wind movement, which is not to say that this is how you simulate wind movement, because there is a thing to apply a wind force as well. But you will notice if I now increase the drag a good bit, that some of that like randomness and some of that chaos starts to slowly disappear. And very slowly, if you keep playing with this, patterns will start to emerge. So we have a very high noise strength now and a very low noise frequency, as well as a decently high drag, and that will start creating these like very, very nice patterns. I think at this point, what we want to do is we also want to set the lifetime back to something more reasonable, like 5 seconds, for instance. And this is the kind of pattern that you've probably seen a million times in a million different renders, because it, again, is an easy way to make things look complex and organic. It's quite nice. Specifically, then, if we change this mesh renderer from cubes, for instance, to something like a sphere, suddenly this feels like a very dangerous like smoke cloud thing. Of course, we probably could do with doing this with like a sprite renderer instead to make it a little bit less intensive. But this is how you can quite easily create like one of those types of effects. Again, I'm sure that if you're interested in visual effects and like particle simulation, you've probably seen a simulation that is very similar to this, probably a little bit more fine-tuned than what I've just made, because these are quite nice. That is how forces work. So if we add in like a little bit of maybe gravity again, let's see what that does with this, because it's going to absolutely screw with it, I assume. Not even that bad. So this is actually interesting, right? Because our curl noise force is so incredibly strong, and it's getting dragged down by this drag, and we can probably, like, if we halve this drag to like 25, this will start becoming a little bit more chaotic once again. But then if we also halve this to roughly like 15,000, it should be more or less the same movement, but it will now be more susceptible to other kinds of influences as well. So it's more a ratio between these two things than anything else. So again, let's lower this to about 5,000, and then the drag should go to about 8. And now we can start seeing that the gravity is taking a little bit more effect on this system, but it still has that really, really nice shape. And the lower the noise frequency, the bigger the individual like strands of this pattern are going to be as well. And the higher you probably want the actual like particle lifetime to be. So probably set this to 10 if we set the frequency to something lower again. Again, that is kind of like a ratio that you want to be looking into, but that's the basic idea. So we talked about velocity and about forces now. So with this, you can really start working on some interesting stuff. But you can also see that we're like doing like quite a number on our FPS here when a lot of these meshes start spawning in. And that's because we're rendering this entirely on the CPU. I think next time to talk about some more theory stuff again, and we're going to talk about CPU and GPU rendering, because they both have their upsides and they both have their downsides. There's no singular you should just do this button. So last time we made this fantastic, very organic, fun looking particle system, but we can see our FPS is starting to take a little bit of a hit, and that is mostly because this is now spawning in like, I don't know, what is it spawning in, like 500 meshes per second or something like that? 1500 meshes per second. That's a lot of meshes every single second, and it's doing all that on the CPU, so that's not ideal. So what we can do is we can go up in here into the properties, and we can change the sim target from a CPU sim to a GPU compute sim, and immediately it runs so much smoother. But there's a few little issues with this, and that is to do with the fact that, and I'm probably not going to make a specific video about this, but if you simulate something on the CPU, you can have collision, because things that happen on the CPU are like physically present in the world. It can have interaction with things that are also physically present in the world, such as colliders. GPU particles aren't physically present in the world, they are just being rendered there by the GPU. The GPU doesn't know what is going on the CPU. All that the GPU does is it just takes in a bunch of data, calculates a lot of very tiny things very fast, and pushes out pixels to your screen. GPUs don't do collision, they don't do like a lot of logic, they just are really, really good for rendering. So if you have something that's complex to simulate or complex to render in and of itself, this is messing up a little bit, GPU particles might be necessary. But there's a couple of issues. Because these only are kind of like another layer rendered on top of the actual game world, almost. It's not quite how it works, but almost. They will only be able to be visible within a certain bound. Which is to say, because they're not physically present in the world, the GPU needs to know when to simulate and when to render these things. Because it has no idea where they physically exist inside of the world, otherwise. So here we can calculate bounce mode, and we can set that to dynamic. And usually that's actually pretty good. So let's take this Niagara emitter that we've been using, and we can actually just immediately create a system out of it. And if we put this into the world, it will start spawning in our particles, which is absolutely fantastic. It's also a little bit bigger than I initially anticipated. But you might be able to see if we go up against the edge and the origin point of our particle system is properly off screen, it just stops rendering it altogether, which is not ideal, right? Especially for things that are big like this, that can be a real issue. So a way to combat that is, instead of using dynamic, we can use a programmable or a fixed bounce. And fixed bounce, you can just say, okay, within 100 by 100 by 100 units in this case, in all directions, that also, as long as any of this bounding box is on screen, render these particles, which extends that rendering quite far. So if we can just say, hey, we just want to render this if anything within 1,000 units of the origin point of this actor, is in view. Now we should be able to see that it will still disappear, but it will disappear a fair bit later off of our screen. Like at some point it will. We've actually kind of done it. There we go. It disappears, but it disappears a fair bit later. So that does come with, of course, computing cost, because having that fixed bound means that it's also going to be potentially rendering unnecessarily when it doesn't always need to be rendering a lot of the time. So if we just switch this back to CPU, you can see that it can just have like the dynamic bounds. Now the CPU dynamic bounds are by no means infallible. You can still make your particles like disappear if you like move away far enough from the emitter and look at like a weird angle away from it. You can see that they still do disappear, but it's a lot more robust on the CPU than it is on the GPU. But that's not even the biggest thing with the GPU and CPU difference. The biggest difference between GPU and CPU particles is that CPU particles have the possibility to have collision. Of course, that is quite expensive because there's a lot of collisions happening here. So let's actually decrease the spawn rate here back to like 500 since we're doing this on the CPU. And in particle update, we're going to put in collision. Now, we can say our CPU collision type can be either ray traced or analytics planes. For the most part, ray traced is a little bit more expensive, I believe, but more accurate. And we can say whether or not the collision is enabled or not. And then we've got a couple of different things that we can set what like the collision radius is, how it calculates that. We can just use the mesh for that. Again, that is going to be a fair bit more expensive for obvious reasons. And when it collides with something, it has some bounciness to it. It can have some friction to it. Just normal collision stuff. And what's really cool is this stuff down here, right? You can say when you collide with something, you can advance the age of your particle by a certain amount. So particles that collide with walls will die quicker than particles that are just floating in midair. That's quite cool. Anyway, now that we have the collisions enabled here, you will be able to see that no longer do these particles move through everything. They kind of hang out on this platform and then they fall off onto the ground here, which is where they eventually do end up dying. So it's not like because they have gravity, they stop floating around. You can see these ones still float around without a problem. But these ones, in their path of their force that they're being pushed around in, just happen to collide with something else. And that means that they can't keep moving downward. So the force is still moving them in roughly this direction, but the downward direction, they can't move there. So they just kind of move along the top of this block here. If we set the bounciness to an insane rate, this is going to look very stupid. But I've set the bounciness here to 500, and this is going to, yeah, be kind of wild. That's what that ends up doing, which is quite cool in a way, I guess. 500 is maybe a little bit too much. Specifically with the curl noise force and the drag that I have set up from the last part of this series, things get a little bit iffy sometimes, but 500 is definitely too much. Let's just set this to like 10. And now you can see when they land on the ground, they bounce around and then they get picked back up by the curl noise force, which actually makes for a slightly more chaotic, but still like quite fun to look at kind of particle system. And once again, if I now change this over back to a GPU sim, it's going to yell at me about the collisions. Because now we are using a GPU collision type, which is possible. It is a thing that you can do. It's just a little iffy. Because instead of using the actual collision of everything, what it uses is it uses a depth buffer. And what that means is we have like the camera that renders our scene, right? That's a very good camera. It has a field of view. And we have like a ground here. And we have like a tree, very good tree, very good at drawing right here, right? The camera just renders those pixels to the screen with like the perspective and everything like that, but it is also aware of how far every single like pixel on your screen is away from the camera. So it knows this tree is closer to the camera than this piece of ground. So it can use that, because if it sees, hey, this particle is at the same depth as this tree, that means that they're colliding. So I can calculate collision off of that, and I can like bounce them off of that, and that works for the most part. Except that with a CPU simulation, it uses the actual colliders here, so it collides all over the place. And what that can do, what a GPU particle can't do, is collide from this direction. Because all a GPU particle can do is use the depth buffer of every single pixel that it can see. It can't calculate things that it cannot see, because it's being done on a GPU. This is the huge thing about collision with GPU and CPU. Now, we also have distance fields which work similarly. It just checks whether or not a particle is close to a mesh that is emitting a distance field, and it'll bounce off of that. That works a little bit more smoothly than the depth buffer, I believe. It does have an experimental ray tracing GPU option, which in theory, I believe this is supposed to negate the issue with the depth buffer method, in that this will be able to ray trace on the GPU and fix the like occlusion issue. But it is experimental, so it is probably also prone to breaking. Maybe in the future, if you're watching this like a year from now, this will have been fully developed and everything works perfectly, at which point there's going to be increasingly little reason to simulate on the CPU, but for now there's definitely still a lot of reason to simulate things on the CPU. So for the most part, rule of thumb, lots of particles means GPU, accurate particles means CPU. And that's the difference between GPU particles and CPU particles. And this kernel noise force is still just very satisfying to look at. I can look at this all day. But we won't, because this is the end of this episode. Next time, we're going to be talking about some more fun stuff again. See you then. Today is the day that we change from particles and meshes, and we're going to be talking about ribbons. Because ribbons can do some really cool stuff. But what even is a ribbon? Well, let's make a new particle emitter here. So we're going to go into effects and we're going to make an emitter. It's going to be an empty emitter to start with, and we'll call this our ribbon emitter or something along those lines. Or a Biron emit. That also works. I cannot spell to save my life. Anyway, we've got our sprite renderer here that we are fairly familiar with at this point. And we can put in our emitter update, we can put in a spawn rate, we've gone over all this, and spawn in like 10 particles a second, and have those spawn in with a velocity of some sort. We fix this issue to add velocity forces. Let's send them up in that direction, and then in particle update we're going to add a gravity force, and now we've got this very sad little particle drip effect, right? And we can increase the initial velocity a little bit so that we have like a little bit more of an arc going on there. And that is all fantastic, but what does this have to do with ribbons? Well, I'm going to add a ribbon renderer to this because I think this is going to be the best way to show off what a ribbon renderer actually does. So let's add a ribbon renderer, and in the initialized particle, I'm going to set the ribbon attributes, the width mode, to direct set, and I will increase the width. And you can start seeing there is a line going through all these particles at this point. So what is actually happening here? I'm going to disable the sprite renderer so that it only displays the ribbon renderer. And what the ribbon renderer does is it takes all of the particles in existence, and that is why you can see that it's a little bit like freaking out here, because it spawns in a particle, and then it spawns in a new particle, and a new particle, and a new particle. It connects all the living particles together, by default from newest to oldest. So again, as it spawns in new particles here, the start of the ribbon gets reset and gets reset and gets reset and gets reset, and that's why it's a little bit weird like that. Now, you can change the drawing direction here in the ribbon renderer itself. We've got sorting, which by default is front to back, which is, again, the newest particle to the oldest particle. But we can also change this to back to front, which actually just kind of looks the same. But if you have a specific material which is orientated a specific way with the UVs, this might matter. It might not. For the most part, you can probably leave this alone, but it's good to keep this in mind. We have a couple of other things here, like the mode, which is automatic, custom, or disabled. This is the ribbons tessellation. So the way this works is, even if we have very few particles, because we're only spawning like 10 a second right now, if we get that down to like 2 a second, you can see it's a little bit more jagged, but if we turn on the sprite renderer again, there still is some curvature in between every single one of these particles. And that is because it's being tessellated, meaning that it's getting extra like geometry added to it in order to render more smoothly. We can set that tension of that curve to being much higher so that there is no curvature there and it's actually only straight lines. So at a value of 0, it's a very smooth curve once it has enough particles to make a smooth curve, and at a tension of 1, it is just a straight line. You can also change the shape from a plane. We've got multi-plane as well. You've got a tube, which that one is actually potentially interesting. It looks pretty much the same though, if I'm being honest with you. So for the most part, setting this to plane is probably all that you need. Now that we understand a little bit more about ribbons, I'm going to get rid of this spawn rate, and we're actually going to spawn per unit. We talked about this a little bit before, and it was really hard to really show off how this is useful and what this does. But now that we have an understanding of ribbon renderers, let's apply this and make this into a particle system instead. So we create a new Niagara system. If we put that into the world, you can see every time we move a certain amount, and I probably want to decrease the velocity and the gravity force as well for the sake of this example. But now every time we move in, I think by default 20 units, it's going to be spawning in a new particle, which means that's actually quite nice. Now, probably want to space this out more like 250 units. Or even up to 1,000 units, whatever. And now back in the viewport, if we move this particle system around, you can see as it moves, it spawns in new particles. It's a little bit weird in the viewport itself, but if you end up like parenting this to, for instance, a sword or like a character that moves around as like a speed trail or whatever, that's the kind of thing that this is really, really useful for. It will behave a little bit better than dragging it around in the viewport. If we simulate here, it will also behave a little bit more smoothly, but you can see this is how we spawn in these particles over a certain distance. So that's quite cool that you can use that kind of thing. Now that we understand this ribbon renderer properly, as well as having gone over the spawn per unit, we're going to talk about beams, because that is something that you're going to combine ribbon renderers with quite often. So let's, for the most part, just stick with the sprite renderer as I explain what a beam is and how we can spawn it in and how we can set it up. And then we're going to change over to the ribbon renderer for the actual result that you might want to be looking for with this kind of thing. So in emitter updates, we can add a beam emitter setup. We do this in emitter update because you can, if you want to, change this throughout the lifetime of your emitter. And this is going to take in a beam start position, which by default is just 0, 0, 0 in local space for this particle system. And that is going to take in a beam end position. For now, let's just set that at like 150 to the X. You can also do it in the Y, in the Z. You can do some interesting stuff with this. Then when we spawn particles, we're not going to spawn in a shape location or whatever. We're going to be spawning in a beam. So spawn beam. That's going to take in the beam emitter setup that we have here and spawn in particles on it. Of course, we don't have any particle spawning set up at the moment. So let's go back into our emitter setup. And for beams, you really only ever want to use spawn burst instantaneous. And that is because if we do that, you will be able to see we spawn in 1 particle. That is a little bit too little. So let's spawn in 10 particles. There we go. We can now see these. It spawns in the particles all at the same time across the line that you specify for your beam, which is going to be useful in a moment. Trust me. In much the same way that in a shape location, if you want to evenly space out your particles across the space, that only really works when you spawn them all at the same time. Because if you're spawning all the particles one at a time, it's always going to, well, evenly spread them out over the beam in the context of every single particle on its own. So we can just show you how that doesn't really work. If we set this to a spawn rate instead, it's going to, let's set this to like 15 particles per second. It's always going to spawn every single particle at the 0 position, because it's not taking into account the particle that previously spawned or anything like that. It's just going to be spawning at the 0, 0 position. So for beam spawning, you want to use spawn burst instantaneous. As you can see, it spawns them all neatly in a line. And again, as we just talked about, that's exactly what a ribbon renderer will show you. So if we disable the sprite renderer here and we enable the ribbon renderer, we can now see, hey, we effectively just spawned in a line. Now, the default material here for these lines is a little bit, how do you say it, boring. So let's maybe go into our particle update and we can scale the color, right? And we're going to scale the color with RGBA in linear color curve, and we're going to set the alpha here to a value of 1 as well, so that it doesn't necessarily fade out as much. It still does fade out, and that is to do with the material itself, I believe. So yeah, this material specifically also fades out the texture coordinate. So you can make a separate material here. I'm just going to get rid of the texture coordinate fade because I don't want to be using it. Don't change this material in your own project, because this is a great default material to fall back on for ribbons. Just make a separate material that only does this, right? For now, we're just going to stick with this change material because do as I say, not as I do. And now you can see it doesn't at all fade out. It's just a white line, which is quite neat. So let's do something with these colors. We're going to maybe start at a blue color, and then we want to end at a magenta color, something that is nice and different so we can see it. And this is just going to change over the lifetime of this entire strip. So the strip as a whole is now changing its color, but that's not exactly what I wanted. What I wanted is actually for the strip to start over this side blue and then gradiently change into the magenta color, not over a lifetime, but instead over the distance. And the reason that it's doing it over the lifetime is because we're telling it to, right? We've talked about this in a previous video, and that's this curve index. That is the value that talks about like this direction, that's a very straight arrow, of your curve, or in this case, your gradient. And that by default uses the normalized H. So let's take a look at what else we can use. There's a bunch of different stuff that we can use here, but what we want to be using is the link order. So this is for the ribbon. We can use the ribbon link order. There's like 3 different ones of them. I believe we want to be using this one. So now you can see where the ribbon starts on the right hand side, the first particles that spawn. Well, they all spawn at the same time, but they still do have a order that they spawn in. And so now here we have a gradient in which we can actually just put in other colors as well, right? If we want to say, actually halfway through I want you to turn green, and then I want right over here I want you to turn like a little bit white for a moment, we can start making this little color strip, which is quite nice and quite fun. In the particle update we can also scale the ribbon width if we wanted to, and here we can get float from curve, and there we can, again, this is over the normalized H, so it just shrinks down. Once again, if we use the link order instead for the ribbon, now we can really quite nicely say, okay, at the beginning of your lifetime, or the beginning of your link order rather, you are very wide, and at the end you are very narrow. And that's how you can do that very easily. And you've got these like very standard looking curves that you can use, which are all nice. This is quite nice, but since we're working with a beam spawner, which is a very specific spawner to do this kind of thing exactly, Unreal actually offers us some tools to do this specifically with beams. If you have simple different particle systems that don't use beams but do use ribbon renderers, this is the way that you would do it. But since we're working with a beam here, we can actually get rid of the scale particle ribbon width thing here, and what we can do instead is in the particle spawn, when it spawns, we can set the beam width. and that effectively does the same thing. So we can set the beam width. We also have a twist amount, which is quite interesting, but we're going to ignore that for now. And we can get a float from curve here, and again, this more or less just kind of does the same thing. We want to set this to the link order, but now it's setting that value specifically to do with the beam. As far as I'm aware, they're fairly the same thing. I'm just giving you both options because this works with a beam, and this is the way that the Unreal particle systems themselves do. Like the beam template that they have, they use the beam width and then also an update beam function here. So that's a good way to do it, but that only works if you're spawning in a beam. If you have a ribbon renderer on something that's not a beam, you're going to want to do it the way I showed you. But I personally think it's just better to scale the ribbon as like a standard workflow, so you don't have to think about it too much, because I don't know that the beam width module itself has much else going for, other than of course this beam twist amount, which is actually like quite interesting. Because if we also get this from a curve, which we're going to take the link order, which we will just like copy and paste over here real quick to get that value. Like you can twist this beam around a little bit, and that makes for a potentially interesting effect that is something that you can really only do with the beam renderer. I'm sure that you could replicate it some other way, but this is an easy way to accomplish that. So for this very specific effect, using the beam width is interesting. Otherwise, I wouldn't worry too much about it. Now, the one last thing that I want to show you, because it's a often shown and used effect that is quite easy to set up and quite easy to make with ribbon renderers, and that is let's get rid of this beam width real quick, and we're going to set this to scaling the ribbon width again, because again, that is the way that I prefer to personally do it. Your mileage may vary. So let's paste in that value for link order again, and we've got that going. What I will do is I will add some keys to this. So what I want is at the beginning and the end, I wanted to have like a pretty sharp like cutoff, but everything else should be decently straight. And then we can go back into the initialized particle and set this to a significantly lower value again, something like 5. And we've got something a little interesting to look at, like almost like a lightning bolt kind of shape. And that's kind of what we're going to be doing here, because in the particle update, what I am going to do is I'm going to jitter position, and you will see that that does exactly that. It just jitters the position of every single particle around. Of course, we want to jitter this a lot less. And here we get into a little bit of fine-tuning, because they are getting really far out of place, and that is because every single update, it's offsetting every single particle into a random direction, and that kind of makes all the particles float apart. Again, if we turn off the ribbon renderer and we go into the sprite renderer, you can kind of see what that does. It really starts like pulling all these particles apart. The way to fix that is just to go back into initialize particle and set our lifetime to something much shorter, something like 1 second instead. Now, after a second, that does mean that they will die. And the easiest way to fix that for preview purposes is just to pull this timeline red flag over here all the way back, so that it like properly loops around a little bit better. So there's still a little bit too little detail in this, and that is because if I set the sprite size real quick to uniform and I scale this to like 2, and I set the sprite renderers to being on again, these are all the points that the ribbon can work. There's not much more to it. Also note, by the way, that it's not just the ribbon that gets colored, it's the particles, the sprites themselves get colored as well, based on the scale color still, so that's quite nice. But if I go back into spawn burst instantaneous and I set this instead to using 50 particles, let's go back to the ribbon renderer and see what happens. Like, we have a much more like detailed wiggle in this. It's still not exactly looking like we want it to look like, and it's partly because 50 is just too much for this. So that's like 20, maybe 30, it'll probably be enough. And here we start tweaking values. So I'm going to jitter amount a lot more, and then we're going to go into initialize particle and make them live a lot shorter. And we're also going to be setting the ribbon width to something even small. Now, there's one last issue that I really want to take care of in this, and that is the fact that the ends also move all over the place, and we don't actually want that. So we're going to set the jitter amount to being taken from a curve, and by default, of course, that's going to take the normalized age, which means that they're going to start out not wiggling a lot, and then as they get older, they wiggle more and more and more. That's not exactly the way that I want to do it. What I want to do instead is I want to, of course, use the link order here for the beam. Meaning that at the start and the end, I want them to not move at all. But then I want to add 2 extra keys, one there and one there, where they start moving. So now if we play this, and I think I set the lifetime to 0.2 or something like that. So you can see the beginning and the end now don't move, which for like a lightning kind of effect feels a lot better. I want this to be a little bit more emissive. So we have this scale color. It's a little bit annoying to increase the values on one of these gradients. An easiest way to fix that is instead of using the scale color, we can go into particle spawn and we can just add a color node, and here we can say, hey, we've just got our normal color, but we can get a multiply linear color instead, which will just give us our tint that we want to apply to this. So we can tint the entire thing like more blue if we want to, and then everything is going to be tinted more toward blue. We've talked about this in the past. This is just going to stay white for now, and the scale factor, we want to get our vector for from a float. So it's just going to be one value. If we set that to something like 10, you can see that it starts being more emissive. So maybe even something like 50. And now it starts to feel like a rainbow colored kind of lightning strike. And we can keep going back and forth between all these things, because now I feel like, maybe actually we do want to have a couple more particles in the spawn count to have it be a little bit more chaotic. And if we add in more particle spawns, maybe what we want to do is we want to set the jitter position to a slightly lower value, so something like 0.7. And you can keep tweaking this endlessly until you get the values that you want. But those are the basics of ribbon renderers and beam spawners in Unreal Engine. It's quite important to note because oftentimes, otherwise, what you will end up doing to create something like a line is just spawning in a bunch of tiny square particles, hoping that they roughly form a line, which is just not great to do it that way. So hopefully this has been helpful. Next time, we're going to be moving on with making particle systems a little bit more customizable using, which you can see in the bottom left corner, parameters. And that's going to be a very interesting one. So I'll see you all back then. When we left off last time, we talked about beams and ribbons and sprites and colors and jittering positions and so much good stuff, and we made this like little rainbow zappy lightning strike particle system. And today we're going to be talking about how do we want to like change this on a per instance basis, because if we want to, instead of having this like scale color mess that we have here, say we just want it to be one color. For the most part, that's what like a lightning strike would be, right? Maybe we want to have a blue one and a green one and a red one and a purple one and so on and so forth. And are we really going to like use this one emitter and then make a separate system for red lightning and a separate system for blue lightning and a separate system for purple lightning and a separate system for pink lightning and so on and so forth? Because that might be the way you're thinking about right now, because that's how this works, right? You've got emitters, you can put those into systems with like slightly different values. If you just want to change the value of like a pre-existing module, you don't need to make a separate system with an instance emitter for that. That is going to be a mess. That is where parameters come in. In the bottom left corner here, we have the parameters that Unreal Engine provides you by default. Things like the age, the loop delay, the execution state, whatever, how many loops you've done. We've got a bunch of things about the emitter, how old is the emitter, for the beam, the start, the end, the beam direction. A lot of information that you can use in all of your calculations over on the right hand side here, which I think will make a separate video just going into the more like complex calculations that you can do with all of the stuff on the right hand side as soon as we've gone over like this parameter thing. That is where things get really interesting and really important. So, and then we've got all the particle attributes. So this is on a per emitter basis. This is on a per particle basis. So the age of the particle, the color of every particle, and so on and so forth. Where it becomes interesting for this video is you can add user parameters. It's only supported in systems, not in the emitters themselves. So we've been working inside of this emitter this entire time. We're going to go over to the system version of it, which you can recognize by the fact that it has one of these little system nodes with it as well. And there you can see we can add user parameters. So let's add a user parameter here for the, actually let's apply the changes we made to this emitter so that the system will reflect that. And here we can say, I want to make the color. That's the example that I've been using, right? I want to make the color a parameter. So we can add a new parameter and then we can make new, and we've got a bunch of different types of parameters. And these are just variables for your particle system, right? So the common ones will be things like a bool, a float, integer 32, a linear color, a matrix, Niagara ID, whatever. All of these can be used to your discretion to do pretty much whatever you want, like a bool, for instance. If you want to add like just a tick box for a certain emitter, maybe to do a certain thing, like spawning certain particles at all or not, you can add a bool for that. Or the amount of distance that a particle needs to travel, or the velocity of particles on spawn or whatever, you can make a float parameter for that. The starting position, for instance, maybe you want to do something with that, or maybe it's the ending position of a beam, can be very, very easily changed. For now, what we're going to be doing is we're going to be adding a linear color, and this will be our beam color. And it is really as easy as now going into the color, and where we say, hey, linear color, and this is just a tint, we're going to just take this and drag it over, and we can just drag it over there. And now whatever we set this parameter to will be taken as the input for the color, as you can see right there. So that is a nice central way to influence some things about your particle system, but that's not where it ends, of course, because now if we pull this into the world, we can see we have this little like lightning strike, which will be very, very tiny. We also need to go into its emitter and set its loop duration to being the same as the particle's lifetime. That's quite important. So this is one of those things. We have two things that actually are linked to the exact same value here, right? So the loop duration should be the same as our particle's lifetime, which is in this case both 0.2 seconds. So instead of going back and forth and back and forth and back and forth and back and forth, what we can do is we might actually just be able to get the loop time from this actually. Yeah, I think we can just set the current loop duration in this case, and that will be fine. Just for argument's sake, what we can do is we can just make a new parameter, and we can say like loop lifetime, and set the default value there to like 0.2, and we can just use this user value in both of them. And then I can just change it over here whenever I want, and it will change both of them. Now again, there might be something to the idea of just keeping the loop duration in here and then passing it through to the emitter. I also don't hate that idea, but for argument's sake, let's say that this is just easier to access. And now we can also change it very easily on an instance per instance basis. So as you can see now, it doesn't blink in and out of existence anymore. It just does as like wiggling. And we can see here, we have our beam color and our loop lifetime as user parameters that are exposed to the editor. So right here, we have both of them. And I can set the beam color to simply be like a magenta color. And now this specific instance will be a magenta color. And if I copy this over real quick and I said, actually, I want this one to be more red, we will be able to see that this one is now a more reddish orange color. They're still the exact same particle emitter, the same system. We didn't need to make a separate system for them. They're just separate instances using their own set of parameters. So for this one, I can also say, actually, I want this one to like live for 3 seconds, which means that you can see they like deform a lot more over that 3 second lifespan. Maybe I want it to be more chaotic. So I set this one to 0.1, which means that it wiggles around a little bit faster. So that's all well and good. And we can set these parameters to like a bunch of stuff, which is very, very fun. But now let's take a look at one thing that we have entirely ignored up until this point, and that is the emitter spawn. Because now that we have parameters, we can set those parameters on a per emitter basis, on a per instance basis, to use these parameters to set these values instead. So here we can set new or existing parameter directly. here we can add our parameters that we have, so we can either make new parameters that are specific to this emitter. So if we want something to not be exposed like we just had, but we do want something to like get a random value or whatever, such as the color, we can make something that is only visible within this emitter and isn't an entire system-wide thing. So you can actually make that inside of the emitter itself. But we can also set a specific parameter, which is a lot of the parameters in the default engine we can access. Unfortunately though, you can't drag in your own user parameters. So if you want to have something be assigned like a random value per emitter, for instance, this isn't going to work because these values are here to be exposed to the end user. That is the point of this little window over here. So if you expose something to the user and then the actual particle emitter itself is going to mess with that, there's no real point in that for the most part. You can still use both of those things together to calculate a new output, which I will show you in a moment. But you can't directly overwrite these in set parameters. So instead, what you could do here is you could like make a new linear color, and that will be emitter linear color. We can change the name for that, so that is random color tint, and we will set that to a random linear color. Again, between this like blue cyan color and the like magenta color, or this red even. I'm going to pick a random color between those. So then in the actual color, we have our linear color for our beam, and we can multiply two linear colors together. So we've got our linear color and our scale factor in this case. The linear color that we're going to be multiplying with will be our parameter for random color tint, which is the value that the emitter itself generates on spawn. So in this case, that was this like quite nice blue looking color, and we're going to multiply that, setting our scale factor here to also be a vector from a linear color, and that linear color is going to be our user defined parameter. So it's now going to be taking both of them. It's going to be a random one per emitter, but our user can still tint on top of that a little bit if we want to. So if we copy this one over, for instance, and we set this back to like a little bit more of a white color, we should see that it still has some color to it because, of course, getting a random color applied to it. But we can tint that a little bit. So if we tint that a little bit more toward yellow, that bluish color becomes green because they're getting multiplied together. And if I want to just say, actually, I want to overwrite this with my own color, making my own color like very saturated is effectively just going to override it. Still a little bit of that random color in there. Again, you could set up something where you also have a float value that lets you influence the amount that the initial like randomized color gets mixed in as well. You could set that to 0. Again, I think I should make a video more specifically about this type of thing. Taking multiple values together and using them together to do some like math to create more complex, more dynamic value. But before we do any of that, I want to show you one last thing, because these parameters, these user parameters, you can just set when spawning them in like this. But what if you spawn something in through code, right? If you have a blueprint and you spawn in a Niagara particle, or you even have a Niagara particle component, because that is something that you can do, how do we set parameters through code? Because that's probably something that you want to be able to do. So let's make an actor here, and we'll just call it new blueprint. That's fine. I'm going to put it right over here. Let's add a blueprint. It's a really weird way to add a blueprint, I am aware. And we're going to add a Niagara particle system component. We only have really one system that we care about, and that is this one. And it's getting this like very nice orange, almost pinkish color in this instance. But you'll see every time I compile this, actually, it reruns it again, or at least it should. I don't think it does. It will in actual gameplay. Doesn't do it in the viewport seemingly. But how can I set this beam color? Because I can set that in here now, and that is fine, and it will be more toward that color. It's good, that's fine. So that's not that difficult, right? But say we don't have it as a component. Now what do we do? Say we have on begin play instead, we spawn a Niagara system. Let's say we spawn it attached to this actor. The system template will be this system. And attached to components, we can just say we take our default scene route and we attach it to that. Location can all be the exact same thing, auto destroy, whatever, right? Then we get the output here as a variable. and we can just set a color parameter. Here we need to pass in the value of our parameter. So in this case, let's say that we're going to be making that like a bright green, and the parameter's name. And this is honestly just go back over into your system and rename, copy that name over and just paste it in, because this is case sensitive. This is sensitive to typos. You want to prevent weird issues because you just mistyped something, right? Now, if we have this specific actor here, it spawns in on begin play, and then we'll set its particle system to use the color green as we specified. So that is how you can set these values through code. And of course, we did it with a color in this case. You can set like a float parameter as well very easily, and every single type of parameter that you could be asking for, you can set through these means. So that's a little bit more about parameters. They really enable you to customize particle systems and make particle systems very customizable so that you don't have to like replicate the exact same system a billion times over for very minute differences. Or in some cases, if you have a very like robustly set up emitter and system, even frankly, very complex particle systems can look very different using just different parameter inputs. You can do some really, really cool stuff. But in order to get anywhere close to that, I think we should just do a video, which we're going to do next time, about setting up more complex values. You've seen me using a couple of times the value from curve, and you've seen me like multiplying things a little bit. I think you should do a video specifically about just nesting those different things a couple of layers deep so that we can get some really like deeper math going on to create cool looking systems. Complex calculations for values in your particle systems. This is going to be what makes your particle systems go from just, hey, we have a particle and we shoot it into a direction, into something that is potentially more malleable and more interesting to look at, and just generally, there's going to be a lot of math involved. Don't worry about it. I know a lot of math might sound like a headache, and it very much could be, but we're going to go through this one step at a time. So you've seen me in some of these other particle systems saying, hey, I want to get, for instance, I believe here, the ribbon width. We're getting this as a float value from a curve, which takes a value from this curve here based on the curve index value. And that is the simplest version of what a complex value could be. Well, the very simplest version probably would be just multiplying two values together, to be fair with you. Today we're just going to go through and make something that nests a couple of these little things down in each other so that you can get a little bit more of an understanding of what this module can do and how these modules can like be more complex very, very quickly, which both is a confusing thing sometimes, but also can be really, really nice. So let's make a new emitter for this. Just start fresh. We'll make this an empty emitter, and we will create this and call this like complex emitter or something like that. And here on emitter update, we'll add in a spawn rate. Let's say we're spawning in 25 particles per second. Then on particle spawn, we'll add a velocity. We'll fix issue and add solve forces and velocity. We've done all this before, so I'm going to kind of speed through this. Now, what I want to take a look at is our velocity here, because this is just a vector 3 value, right? It's an x, a y, and a z value. And we can set this, but it's kind of annoying to set these individually. We can like bother with curves and stuff like that. What if we want to just split this up into 3 float values? Because that is effectively what a vector 3 is. It's just 3 float values, and in like coding, it has some functionality together with it, but effectively, it's just 3 values coming together to make like one value that's easier to work. Well, you can actually simply do that. You can make a vector from float, and then we get one single value, right, that we can work with. So now it just spits them out into one single direction. Doesn't really do what I wanted to do though. So we've got a different one, and that is make vector. Not make vector from float, just make vector. And that one supplies you with separate x, y, and z. And as you can see now, the wonderful thing is we created that by using this little drop-down menu. And there you get all the different like calculation stuff that you can do. But now each one of these axes individually, the x, the y, and the z, also have their own little drop-down menus. So you can nest this stuff deeper and deeper and deeper and deeper and deeper until you've reached what you wanted. I do want to pay a little bit of attention to a slightly maybe more complex way to do it in some ways, but once you've learned it, it might be a little bit less complex to do it. We're not going to be using this way that I'm going to be showing you right now, but I do want you to be aware of it. And that is, you can make your own scripts. So in this case, we have a input, then we just get the x, the y, and the z value, and we output, right? That's just a script that the engine provides you with. You can make your own scripts. We talked a little bit about them before. In the FX, you can make a script, and there you can make a Niagara module script, or a function script, or a dynamic input script. Again, I feel like for the most part, this is unnecessarily complex because you now need to start learning like all these new nodes. And while that can make some of the things that we're about to do a little bit more smooth and a little bit easier and more reusable, because once you've made one of these scripts, you can very easily reuse it in different places inside one emitter, inside multiple emitters, inside a system. So I might do some videos on this in the future, but it's probably going to be as part of like a Niagara intermediate course instead, because this is an entire like subsection in and of itself. What we're going to do instead is we're just going to nest the ever-living hell out of these individual values. It can be a little bit bothersome and a little bit cumbersome to read once these become like very complex. So at that point, again, it is worth trying to like learn how to make these scripts instead. For now, we're just going to do it the simple, straightforward way. So let's get started. We want the x value to be a range of a minimum value to a maximum value. So let's get started with that. We can get a float in range, random float in range, and here we can say we want that range to be -1 to +1. And that doesn't really do anything until we set the velocity speed scale for the velocity itself to be higher. And now we can see in the x direction, if we set this to like 10, maybe 100, every single particle is getting, in specifically the x direction, a random value applied to it. So some of them are going to be shooting out faster, some of them are going to be shooting out slower, some of them are going to be shooting out like not at all, effectively. And we can kind of like copy that over. So we can just copy over what we just did for the x, and we can put that in the y as well. So we can paste that. And now every single particle is spreading out in a two-dimensional plane in its own different direction. And then if we set the z to always being like 1, we get something kind of like this, kind of like a cone shape that we're creating, right? And you can already see that we're making like these separate values that we can do stuff with, and it's very, very fun. Obviously, I would probably prefer to also have this be a random float in a range. So let's paste this in here, but instead between like 0 and 1. And that creates a slightly more interesting shape. And now we can very easily say, okay, but we want to maybe actually set this to 0.5 to 1, so it's always a little bit more upward, and none of them spread out very two-dimensionally. They always have some upward movement. And then on the particle updates, of course, we can start adding some gravity to this, and that creates something where we need a lot more velocity on initial spawn. So let's set this to like 750. That's maybe a little much. Maybe back to like 500. And we're starting to make our own little fountain here. Now, clearly, this can use a little bit more work, right? So let's actually see if we can make something that hooks into something like a parameter. So let's go into my particle or emitter spawn, rather, and we can make a parameter. And we will make a new float parameter, and we will call this by renaming it spread. This is just going to be how far these things spread out. So the default value is going to be, let's set it to 0.5 instead. And back in add velocity, we can now use that spread value. So instead of using just the minimum of -1 and the maximum of 1, we're going to be using a maximum of spread. We're going to be doing that for the y as well. So again, look up spread. And then these minimums are going to need to be calculations of their own. So what we do is we simply get another one of these multiply float nodes, and this is going to just multiply our parameter spread, which we have right here, by a value of -1. And again, we can just say, hey, we want to copy this calculation that we have right here for the minimum, and we're just going to paste that right here into the minimum of the other one. And now we have a single value that we can just change here. I can say the spread here will be 2, and now they spread out much further. If I set the spread to -1, they almost don't spread out at all. And that's because it's now just using a parameter or a variable in these calculations to decide all the like random directions that we have. And it's just a much easier way to control what your particles do rather than having to go into each module. And again, once it is set up once, you can see there's like a lot of nesting going on here, which makes it kind of difficult to read, which again, there you go into the maybe making the script is more easy to read once you get into some more complex calculations. So do keep that in mind. But maybe just as like a weird idea, in the emitter update, we can also set the parameter to a new value. And what we're going to be doing is we're going to get our spread value. So we can just add our spread value. And here we get into some interesting stuff, right? Because we have our spread, but we also have the initial value of spread. And this is quite interesting because this is going to never change. This is always going to be the initial value that we give it in this setting of particle spawn. That's what initial means. But we can still update the spread value of the emitter in like either in particle spawn on a per particle basis or in emitter update as I'm doing right here. So what we're going to be doing is we want to set spread to a multiply float of the initial value of spread. So we get spread and then the initial value multiplied by the emitter's age. So now as the emitter lives longer, the spread is going to be spreading out further and further and further. And it will loop after about 10 seconds in this case, which will reset it back to the start. But you can see how this makes something a lot more dynamic. So now this spread does influence how far these things spread, but that is then in turn influenced by how long this emitter is around. So if I put this just in a world instead, so let's put this in a system and we're going to put this into the world, you'll be able to see that the longer that this lives, and I do need to actually set this to apply and save it, otherwise it's not going to do anything. But the longer that this lives, the further these are going to be spreading out endlessly and endlessly. So this is a example of something that maybe you don't want to like infinitely have around, because these particles are going to get like very, very speedy, very, very quickly in a moment here. But you can have a lot of fun with some very interesting values that you can play with in these particles. Again, at this point, the particles are literally already kind of flying out of there. So maybe in order to make that a little bit more like consistent, what we actually want to do is the velocity. We want to have this random range float, which again, we're going to copy because we're going to be pasting it back in because I want to multiply this float by the age of the emitter as well, and then we're going to be pasting in the thing that we just copied over again. It's a little bit annoying that you have to do this. I wish that it wouldn't do it this way, but it's just kind of how it works. And now it's also going to be spewing these particles out higher, higher, and higher, depending on how old the emitter is, which again is going to increase in value fairly quickly. And as you can see, it's already like shooting them like into the stars and beyond. So there's some fun stuff to work with there. I'm going to disable this because I feel like at some point that's going to crash my engine and I don't want it to do that. If you want to check out something that does like even more of this like nesting and nesting and nesting, I have a tutorial that walks you through creating like a spiral like galaxy-like particle effect, which doesn't use velocity or forces at all. What it does instead is in particle update, it rotates around point, so it sets the location directly, and it does like a bunch of math like this to decide for each individual particle where it should rotate it towards. So it rotates it around a center point and then also moves it away from that center point based on like a couple of different calculations, a couple of different like randomly generated values. It's a very, very good example of something that you can do with this like more complex value math. So I think I'm going to probably insert that video into the playlist for this series as well. If you're watching this as it's coming out, do go just check it out on my channel. If you're watching this in the playlist, it should be the next video up. I don't think I will include it in the full series supercut, but maybe I will. I don't know. We'll see. If you're watching the full series supercuts and the next video is not about a spiraling galaxy-like particle effect, but instead about, I don't know what the next video is about, anything else, just do go on the channel and look something like galaxy, and it should be fairly easy to find. I think it is a good exercise to really get into making these more complex values and starting to get a feel for how all that works. Specifically because we're directly setting the positions of all of this instead of relying on all the velocity and forces, which for the most part, when you're making particle effects, you are going to be using velocity and forces. You're not going to be directly like doing a bunch of math to set something. But as an exercise, I think it works out fairly well. And I think next time what we should probably look into is the very reason that I started doing a material series before this, and that is particle materials. We have talked a lot about particle simulation now, but let's look into making the particles also like look a little bit better. And we're going to be doing that by making our own particle material that is a little bit more involved than just, hey, this is a circle and the circle has a color. So I'll see you all back when we cover that. A lot of the particles that we have made so far look sometimes maybe a little boring. Like we've made this little lightning effect and we've also made this curl noise effect, which looks interesting, but all of them still rely on the default materials. And if you really want to make interesting looking particle systems that really take the visuals of your game to a next level, you're going to need to make particle systems with their own materials, or at least custom materials that you use for multiple systems, whatever. That's the entire reason I ended up doing an introductory course to materials before I started with this particle series, because I want to make sure that you guys understand the basics of materials, how UVs work, how multiplying colors works, all that kind of stuff before jumping into this, because everything we've done so far has just been about simulating the particles and effectively just giving them a position. Visualizing them is done 90% through the material. We can set up a lot of data inside of these simulations, but then how it actually gets interpreted and used in the material is what makes your particle system look the way it does in the end. And that's what we're going to be looking at today. So let's make ourselves a new emitter here. So we're going to go in Effects, Niagara emitter. Let's start with the omnidirectional burst in this case. And we'll call this the material viewer, because that's what we're going to be doing. We're going to be viewing materials. I'm going to change a couple of things right off the bat though. I want to disable the gravity force. I want to not scale the sprite size for the time being. I want the initialized particle size to be like a fair bit larger, so that's like 25 to 35, and that is a little bit better already. Did I say scale sprite size to 0? I did. And now we've got something that we can work with. So if we go into the sprite render, we're going to be doing all this based on sprites. Of course, it effectively works the same with meshes, because everything in the materials is just going to take this same information and apply it to the meshes output instead. We're going to do this with a sprite renderer because it's just a little bit easier to get into. We have our default sprite material. If we open that up, we can see it has a two-sided sign, which is just to make sure that it renders on both sides, which it does fairly well. Also, this is now rendering on a sphere. When you're displaying particles, usually you render it on a plane. So we have that going for us. It uses the particle color, and then it has a sphere mask here, which could probably just be a gradient instead. I don't know why they use a sphere mask, but sure. This is the default sprite material, and we're going to be making our own that looks a little bit like this, but has some more going for it. So let's make our material here, and we'll call that new sprite material. I'm just going to steal the sphere mask here. Again, I think using a radial gradient makes more sense, but sure, let's go with the sphere mask. And when we open that up, there's a couple of things that we immediately need to change. Because if we go back into the default sprite material here, we can see it is set to surface, which makes sense because particles still are surfaces. But the blending mode is additive and the shading mode is unlit. So let's go back into our own sprites, or our material rather, set it to display on a plane. And then we've got our blending mode, which is opaque, and our shading model is default lit. If you are working with your materials and you feel like you need to have a lit material, something that interacts with the lighting, you need to have something opaque, go for it. 99% of the time, you're going to want to have that additive and unlit setup. And the reason for that is that creates those little see-through particles that when you add and layer them on top of each other, they start becoming more and more and more and more bright as well. And you use the emissive color output for them. So let's put our sphere mask into the opacity and then just real quick set our default color value alpha all the way. I don't think alpha actually matters in emissive color. It might, I don't know. And I'm going to set the hardness for this to being like 0.9. So it's a little bit harder to look at. Well, it's not harder to look at. The edges are just harder, which makes it nicer to look at, as a matter of fact. Anyway, you can see that it is culling the back face. And the way they fix that in the default sprite material is using the toSign node. That's fine. That works. It's probably not going to be an issue because most of the time when you're using sprite-based particles, they're going to always be aligned to your camera. So you don't need to render the back face. Personally, when you do, I like to just set this as a two-sided material, and that way it just renders on both sides. So make of that what you will. We're just going to keep it as one-sided because it's slightly easier to render, especially if you're spawning like 1,000 of these, right? It does add up at some point. Now, let's set this as our new material here, and we'll start working with that. So new sprite material. We do need to apply our settings to it. And let's just try to set our particle color, right? So in instantiate particle, we can say, I want a blue particle, and it's not doing anything anymore. And that is because we don't have any particle color. We are setting our emission color, our output color, just straight to white. Unlike our default sprite material here, which uses the particle color node. So let's look for the particle nodes. And there is a bunch of them. And when I say a bunch, I mean a bunch. We have the particle color, direction, their position in world space, their radius. They all have a random value. Every single particle, when spawned in, gets a random value between 0 and 1, which you can use in materials, often for like offsetting textures and that kind of stuff. Their relative time, which I believe is just a normalized age. Their particle size, which is different from radius. We'll get into it. There's a bunch of these things that you can use. For now, the most important one, of course, is going to be the particle color. So we can just hook that up into here. And then our sphere mask, we multiply that by our alpha from our particle color. And this effectively just makes the default sprite material again, but it also multiplies the RGB with 0.15. It does like some stuff here, which I honestly don't care about. This is a much more simplified version of the same thing. Now, let's say that instead of setting our particle color, we want to also then tint that with a like blue to orange color tint on top of the particle color as the lifetime goes on. So the way we could do that is we could just take this and either multiply or add to it. I'm going to just add to it because it's a little bit simpler. We can do that into the emissive color, and then we can get a lerping node here. And we're going to be lerping over the lifetime. So we can, again, get our particle, and that's the particle relative time. If you're not sure what that node does, you can hover over it with Control and Alt, and this says particle relative time outputs a number between 0 and 1, representing a particle's age, 0 being the moment of birth, and 1 being the moment of death. So actually, as I started recording this, I figured that this is what it would do. I wasn't 100% sure, because I've been using it like that for a while, never actually bothered to look it up for sure. It is just the normalized age. So that's going to be going into our alpha here. And then what we want to do is we want to add two constant colors. I think I said blue to orange, right? So let's make this one blue. And then at the end of their lifetime, they're going to be orange. And they will still have their other color added on top of whatever this is. Really, what you probably want to do is you want to then divide this by 2, just so that you don't like overexpose it. And now you can see they start out as being blue, and if we just go into the scale color and we don't scale the alpha real quick, you can see that they will toward the end of their lifetime become more orange. But our particle color still will work. So if we go into our initialized particle, it's because they start out as blue as well. If we just start them out as white, you can see that they fade more from blue into orange. But we can still, again, apply these colors to the particles and they will get a little bit mixed together. So that's quite nice. That's the very basic stuff that we can do. But what now? We're still just fading them out very boringly. These things are just literally still circles. We want to have a little bit more definition to them, right? So that's where we start putting in our texture samples. We're going to be using a standard Perlin noise. And here we're going to be doing some wacky stuff, which is always fun. I like working with particles because you get to do weird stuff and it ends up actually looking kind of cool. If you do weird stuff in code, your game breaks. If you do weird stuff in Blender, in modeling, your performance dies very, very quickly. If you do weird stuff, like if you do very weird stuff in particles, your performance still takes a hit, but you get away with a lot more, and usually it ends up actually looking kind of cool rather than breaking everything inside. So that's why I like working with particles. So we're going to be using this alpha value, and we're going to be kind of lerping through this texture. And the way we do that is we subtract the texture from the alpha. And that is then going to go into this multiply node instead. So we have it at the bottom here. And that's going to make it kind of disappear right off the bat halfway through though. Because of course, if we have an alpha of 1 and we are subtracting the texture from it, obviously we're not going to be fully opaque anymore. That just makes sense. But what this will do is if we go through here and we actually let's increase the size of this texture by going in and adding texture coordinates for it at like 10% of the size, so that it's a fair bit bigger as a texture. And then if we put on in the scale color the alpha again, you'll see that it kind of scales out in a much more pleasant way right now, right? It uses that noise to kind of lerp through the noise as a alpha matte, which is really, really nice. But it starts already halfway faded out, and that is not really, really nice. So the easiest way to fix that is to multiply this by, honestly, any value, at least a value of 2, because that makes sure that the alpha that we're using as a input, when it is full, is going to be a value of 2. And even if we subtract the brightest out of the brightest pixels of this texture, it's going to still have a value of 1. So it's still going to be opaque, at least as opaque as a additive material can be, as you will see. But as the alpha itself starts to approach 0, the influence of the subtraction from this is starting to be more and more and more. So you can actually set up kind of like a influence curve. If you multiply this by like 4, this won't start being influential until very late into the alpha curve. It's much easier to just set that up with a literal curve though in the material. So just multiply this by 2 and leave it at that. And now the particles spawn in as full circles and then they disappear in this much more noisy way, which makes them feel a lot more interesting to look at right off the bat. Like this much detail and this much extra stuff going on, if you were to simulate this with individual round particles, you would already be spawning in millions of particles for something simple like this. Relying on some material stuff makes this a lot easier to do. We still have a couple of small issues, that being they all have the exact same pattern when they fade out, which is not nice. And there's still a little bit of an issue with the noise itself also scaling up with the particles. So we should probably look into both of those things. Well, the first thing that I want to look into is giving them all a unique pattern. And that's actually remarkably easy, because what we can just do is we can get that particle random and just use that as an offset. So we're just going to be adding the particle random to our texture coordinates. And now all of them are going to have a random offset in the X and the Y direction. And they're going to, as a result, all have a slightly different pattern that they use to fade out. And immediately you can see how much more organic this looks. For the next thing, I'm actually going to increase the sprite size even more, and we're going to use scale sprite size again, and I'm going to scale this up by like 4 times so that the sprites are nice and big. And you can kind of see, actually, I'm probably going to set the spawn burst instantaneous to just 1 sprite for the time being, and I'm going to give it no velocity and no drag, so that it just spawns in and then disappears. If we make this scale up and then set its lifetime to a little bit longer as well so that we can actually properly see what happens here. If this scales up, you can see it also scales up the noise texture, which can be fine, but sometimes maybe what you want to do is, because you want to imply that it kind of like fades into the air, right? It fizzles out, kind of like a flame, or I always think more about soap bubbles when I see this kind of pattern. So we want this UV to scale with the size of the particle. Well, wouldn't it just happen to be that we have a particle size node? We also have a particle radius node, and I want to talk about both of these next to each other real quick, because you might think, oh, we use the particle size, but if you Control and Alt, you can see that particle size is an expression of the X and the Y size of the particle sprite. So this is actually a vector 2. This has 2 components to it. The particle radius is just a float value. So for what we are using it for right here, I'm going to be using the particle radius because it makes a lot of the math a bit more straightforward. You can use the particle size, at which point you could like start making squished and squished and whatever rectangles that still display this texture properly, because the texture is then getting like opposingly squashed and stretched and whatever. You can probably figure that out on your own. We're just going to stick with the particle radius for now. The particle radius we're going to divide, or rather we're going to be using that as the divider. We're going to be dividing 1 by the particle radius. So if our particle radius is just 1, the output here is going to be 1. If our particle radius is 10, this is going to be 1/10 or 0.1. If our particle radius is 50, this is going to be 1/50th or 0.02. So the larger this value is, the smaller the value coming out of this is. And if you remember back to our UV math video in the material series, the smaller this value is, the bigger our tiling is going to be, the bigger our texture is going to appear as. So that means that the bigger our particle is, the bigger our material will display, which means that it effectively is just going to display it as if it was in world space, at least as far as scale goes. Now, you probably do actually want to divide this by another number, like let's say like 250, as just a general like scaling number. But then we need to also get these textual coordinates and this particle radius stuff all both together into this divider before that goes into the texture sample itself. So how do we do that? Well, we can simply just divide them by each other as well. So we take the textual coordinates and we divide it by our particle radius thing, and if we put that into here, that will then make everything. I set this to 5,000 to test off screen. That's way too too big. Let's set it back to like 200, like 100 maybe even. And now you can see the noise texture does actually properly scale up with the particle. There is still the issue that it scales up a little bit weirdly. It feels like there's a little bit of sliding going on here, which is, why does that happen? Well, that happens because it scales it from the top left position. So when it scales up, it's actually scaling in this direction, creating that sliding. We want it to scale from the middle. So what we want to do in our UV space is we want to say, hey, our UV space doesn't start here. It starts 0.5 offsets in both directions. And the way we can do that very, very easily is just take this and we add a subtracting node here. We're going to be subtracting 0.5 from it so that we can divide that. And the reason that we're subtracting instead of adding here is because of the division node. We want this to not get too big as a value. And now you can see there is not much sliding going on anymore. There's still a little bit of sliding going on due to just simple like movement and stuff like that, but the moment we start adding in back our velocity and our drag and we spawn in like 50 of these guys again, we can start seeing that maybe we even want to initialize the particles to only be like 1 to 2 seconds long, and we can start seeing that we kind of have this weird fireworks soap effect going on now. And with all this, you can see there's a bunch more things that we can do. We can maybe set a color fade based on the speed of a particle. As a matter of fact, let's just do that, just have a little bit of fun. So we have the particle speed, and instead of using our relative time as the alpha for this loop that we set up at the beginning of the video, let's do this as the particle speed divided by like 100, because this is not a clamped value. Like the relative time is. If you just go over this, this is just the current speed each particle is traveling. So this is a velocity measured in unreal units per second. So that's centimeters per second. So if a particle is moving quite fast, it's going to be blasting past the value of 1 instantly. So what we want to do is we probably want to divide it by like 150. And then to make sure that we don't mess anything up, we want to saturate it so that it is always between 0 and 1. And now instead of going between blue and orange based on its lifetime, what it will be doing is it will be going between blue and orange. And let's actually set the color here back to white, so you can really see the blue and the orange based on its speed. So we're going to set the lifetime back to something a little bit larger again, and we'll set the drag quite high. So there you can see when these particles initially spawn in, they are orange because they are moving quickly, and then the drag slows them down and their color changes proportional to their speed. Of course, with this type of lifetime, we then want to go back into the scale color and we want to go, hey, we actually want to scale this probably down a little bit sooner and all that kind of stuff. But you get that point, right? So that is particles with materials. Really, if you want to play with particles, you need to understand at least the basics of materials so that you can set up stuff like this to make your particles look a lot better. Because again, if you wanted to make the like detailed, noisy stuff, you could just spawn in like 1,000,000 particles and make something that looks similar to this effect, no doubt. But you would be over-engineering it and it would be underperforming. And you could only like literally spawn in one of them before your computer melts. So the value of proper materials cannot be overstated. We've talked a little bit about materials and a little bit about particles and a little bit about parameters, and today we're going to talk about all of them together. We're going to be talking about how to set parameters for your materials from your particle systems. This is actually going to be a very, very interesting thing to do. So let's get straight into it. Ignore all the extra particle systems that you see here in my content browser. This is the 3rd time I'm recording this. I messed up a little bit with recording, okay? Anyway, let's make ourselves a new particle emitter here. So with FX, Niagara emitter, we're just gonna make that a fountain, why not? And we'll call this fountain something like dynamic param emitter, just so that I know what it actually is. And we'll have our default fountain here, which is just wonderful. And we're going to make a special material for this in a moment. But first, what I actually want to do is, just to show this off a little bit better, I'm going to replace this with a mesh renderer. So we're going to be rendering a mesh, and the mesh we're going to be rendering, let's say those are going to be spheres instead, which is just fantastic. In there, let's make ourselves a new material for that. So that will be our mesh particle dynamic material, or whatever we want to call it. And unlike the previous material that I talked about, which was going to be like additive and non-lit, this is just going to be a normal material that we're going to be rendering on our particles, because that's the easiest way to show off dynamic parameters, to be honest with you. So we'll just simply add in a quick particle color here so that we can hook that up into the base color. And a little bit of a useful tip here might be, instead of using the blend mode opaque, you want to use the blend mode for translucent, so that we can put this into the opacity, like the alpha, right? But translucent materials, especially for particles, tend to be quite expensive to render, because they are more expensive to render to begin with. But then when you have an object that is translucent behind another object that is translucent, your GPU absolutely loses its mind. It doesn't like that. And that is what happens a lot with particles. So instead of using translucent, that is one of the reasons that we usually use additive. But we want a more normal surface renderer here. So what I'm going to do instead is I'm going to do this with mask. You'll see that mask doesn't really support opacity, but we can put this into a dither temporal AA, which is going to dither this opacity. Mask will only allow a pixel to be fully opaque or fully transparent, so it's a lot easier to render. You don't get that overdraw issue with objects behind each other, and you can just put that into the opacity mask. So now it's going to interpolate very, very cleverly with the alpha putting in what kind of dithering pattern it needs to create to simulate that kind of translucency. So I'll actually, oh, this is the default value. Fantastic. So if we zoom into this a little bit, you can see that there's this like little moire effect going on, and that's because it's a very, very tiny pattern, which if we look at it a little bit from a distance, we can see through this. There's not a single halfway see-through pixel here. This is entirely built up out of pixels that are entirely opaque or entirely transparent. That's a little bit of material stuff for you, even though this is a particle series. So this is going to be the basis of our new material. So let's actually go back into our emitter and override materials, and we're going to set the override material here to being our mesh particle dynamic. And you can see that it does have a little bit of a strange fade out effect. The further we are away, the less of a problem this is. It doesn't quite look the same, but this is a million times easier to render than translucency. Anyway, what we're going to be doing is in particle update, I want to add a dynamic material parameter. And here we get 4 sets of 4 parameters that we can pass through into our material. So we have index 0, index 1, and if we enable it, you can see that we have 4 values there as well, and index 2 and index 3. So that's a total of 16 float values that we can pass through into our material. For the most part, that should probably be enough for a single emitter. You can even disable individual parameters here to save just a little bit of resources, because it is putting through that information to the shader, and if you're not using it, you might as well just disable it. And we're only going to be using 2 here, which is going to be parameter 0 and parameter 1, because we're going to be using this for the metallicness and the roughness. So let's go back into our material and set that up, because we want to put something into the roughness and something into the metallicness. So in here we can say our dynamic parameters, and we much the same get our parameter index value. So that is which one of these sets we're going to be corresponding to. For us, that's of course going to be just 0. And then we've got parameter 1, 2, 3, and 4. Combined 1, 2, and 3. So that's RGB. And RGBA is all 4 of them combined into one pin. It's a little bit annoying, and you have to pay a little bit of attention here if you're still getting used to this. The call parameter 1, 2, 3, and 4 here. But the call parameters 0, 1, 2, and 3 here. For some reason, they start counting at 0 on the particle side, and they start counting at 1 in the material side. This seems like an oversight to me, but you're just kind of going to have to deal with it. So we're going to use parameter 1 here and put that into the metallic value, and then we're going to use parameter 2 and put that into the roughness. And then we can apply that, and now we can drive the metallicness and the roughness of our particles through the particle emitter. So if we set this, for instance, to 1 and 0 now, and actually I'm going to go into our particle color and stop scaling the alpha just so that you can see it a little bit better, you can see we are suddenly very, very metallic or very reflective. And then when I set this up to a value of 1, we are still metallic but not reflective anymore, because our roughness is all the way up to 1. And if we set this to 0, we will be reflective but just, or non-reflective and non-metallic, and now we'll be reflective and non-metallic. You kind of get that point, right? So the neat thing, of course, is that we can get these values from curves, just as any other more complex value. Which will make us, let's see, I think this is the roughness, so that should be going down, and then the metallicness should be going up, and that will create this effect where these start as almost like chalk-like spheres in the material, and by the time they die, they are closer to looking like metallic balls. So if we set these keys instead to about 50%, we will see that transition happening a lot sooner, and we can just influence whatever we want with these values. Now, let's go back into scale color and set scale alpha back to true, and we're actually gonna keep the alpha to 1 until the very end here. And I don't know if this is exactly like the kind of particle system that you wanna be using, to be fair with you. Like, this looks a little weird, but it's good at illustrating the point of we're setting these material parameters through our particle dynamically. And of course you can do a bunch of stuff with this. Like we can, for instance, instead of putting our particle color into the base color, we can just make our base color black instead. And our particle color can go into the emissive color here. But we can add a multiplier with the third parameter here. And now we can just set our color as a normal color in our particle system. And then we have a parameter for how intense the emissiveness is. That is separate from influencing the color itself, which might be useful. Just for the sake of being more easily able to animate this. So if we go into our dynamic parameters here, let's just turn off these two because they literally don't matter anymore at this point. If we turn on this one and we set this to like 100, you can see that they're very glowy. And of course, once again, the huge upside here is that it's very easy to do this from a curve. So we start at 1 and we end at 0. If we set that scale curve to 100, we now start at 100 and then they slowly fade out both in their alpha but also in their intensity of glow. Maybe 100 is a little too much to show that. Let's do that at 50 and then maybe let's move this key a little over in this direction, and now you'll be able to see that they stop shining as brightly fairly quickly. Now, there's a bunch of things that you can do, like anything that you can realistically hook up to a material parameter for a material instance. You can also now drive through your particle emitters, and that can be really, really powerful. So just something that you need to be aware of. It's actually fairly straightforward and fairly simple to use. Go have fun with it. I want to talk about death. Well, if this video isn't already demonetized, it will be, because we're going to be talking about killing particles all over the place. And YouTube is not going to understand that properly. So welcome to this video. We're going to be talking about particle death, as you might have guessed so far. So if we look into our previous particle system that we made last time to show off dynamic parameters, you can see that these particles at some point cease to exist. And they have an age and a lifetime. And when their lifetime ends, they die. That is the terminology that we tend to use. But we can also prematurely kill a particle, meaning that if certain conditions are met, we want a particle to destroy itself before it reaches the natural end of its lifetime. So let's just make something that shows us how that works. So I'm going to make, guess what, a new emitter. And we'll call this, this will be a omnidirectional burst, and we'll call this death, because we're just in a good mood like that today. I'm going to turn off the gravity force. For the sake of the video, I'm going to be spawning in like 250 particles instead. And we're going to be making the sprite size like a fair bit larger here, just so that you guys can see properly. And now we have this burst that goes in all directions. So we have effectively two ways to kill particles, and they're both going to, for the most part, be happening in particle updates. If we look into kill particles, we have kill particles and kill particles in volume. Of course, let's first talk about the normal kill particles. This is just a bool. Should this particle be killed? If I set this to true, all particles will be killed every frame. So the moment they spawn, they die. It's not particularly useful, is it? But there we get back to this handy dandy little drop down menu that we've talked about before. And we can set a bool by float comparison. There's also a couple of other different things that we can do, like Boolean and operation, like doing AND operations, or 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 XOR or whatever. For the most part, you're just going to be comparing float A to float B and seeing if your condition is met. And you can of course nest that with a couple of different comparisons and do some like bool logic with that, but for the most part you're just checking, hey, is value A something in relation to value B? If so, kill this particle. So for instance, right here what we could do is we could go into the parameters and we could get the particle attributes, and in here I think we have a velocity, right? So we can check its velocity, and we're going to be checking this in the X channel for now, right? So you can see now if our A, which is our velocity X channel, is greater than B, which is 0, we kill the particle. Which means that anything that is traveling in the positive X direction at all gets killed, and wouldn't you know it, we only have particles moving in that direction away from the origin. And of course we can also set this to Z, which means that we'll only have particles going downward. We can set this to Y, and I guess at this point you kind of like get the message, right? We can set up our own logic to decide whether or not a particle should die. Now, I wish that I could show you that there's also a speed parameter, but there seems to not be. So the way we could probably do that is to just add a bunch of floats together. So we can add float A to float B, and float B will be an addition of floats as well. And if we just add all of these together, and we make sure that they're all absolute floats as well, so that they're never negative. So absolute floats, and then we can get the velocity. So let's see velocity right here. We can just plop that right over in there for the X, and then one for the Y as well. And then we'll also get an absolute float for this one. So absolute float velocity Z. Now it's adding the absolute velocity for the X, Y, and Z. And when that is greater than 0, it kills the particle. Of course, that's always going to be greater than 0. So let's say when it is greater than 1,000, it doesn't kill any of the particles because they never get to this kind of speed. Because we're checking whether or not A, which is all of these things added together, is greater than a value of 1,000. So does a particle travel at a velocity, X, Y, and Z combined, of greater than 1,000? And the answer is going to be no. But now, if we change this to being A is less than B, it's not going to be spawning anything because it's going to be deleting anything under a speed of 1,000. So if I set this back to 0, you see nothing happens. If we set this to like 100, some of the particles start popping out of existence because they get dragged down too much by the drag. Speaking of which, if I increase the drag to like a value of, I don't know, let's say 2, you can see the particles start dying a lot quicker because they're getting slowed down to below 1,000 units of velocity much quicker. This is a very customizable way to kill your particles off, and you can do like a lot of custom logic for this. That's really nice. It's also not the one that I really want to focus on today because I've explained everything I need to explain about it at this point. What I want to focus on, because I personally like it a lot more, is the kill particles in volume instead. So here we can say if a particle overlaps with, in this case, a sphere or a box or a plane or a slab or a cone or whatever, if it overlaps with any of those shapes, we're just gonna kill it. And right now it's killing everything because it's overlapping with them because it's starting at 0, 0, 0. We have an origin offset. Let's offset this to like 150 or maybe even just 50 units in the Z and make the radius for this a little bit smaller. And we'll be able to see if we pay like really close attention, maybe lower this down even a little bit more, that some of these particles will start dying when they start hitting that area. Let's put down the drag back to what it was, and we'll be able to start seeing some particles die pretty soon. There we go. So now some of the particles are dying whenever they hit this volume. We can probably put this back up a little bit more, and so on and so forth. So let's give them a little bit more initial velocity so that they can reach it a little bit more. And then if I increase the scale here, you'll start seeing that we have a little bit of a divot here, because anytime any of the particles reach within this volume, they get immediately killed, which can be really useful. If you have like a plane that you want to set up, you can do a lot of this stuff procedurally as well. Of course, setting it through code how big this radius should be. So when they hit a certain part of a mesh, you can have a kill shape overlapping with that, and then they die when they hit that mesh, and so on and so forth. That can be very useful. Personally, I like using it the other way around. We've got this invert volume. And if we set this just to 0, 0, 0 right now, as long as they're inside of the shape, they will survive. But the moment they try to go outside of the shape, they die. So let's increase the sphere radius here to like 250 instead. And you can see that this creates a very clean line where they will die, because of course we're doing this in a sphere shape. If we do this in a box shape, you will see that they die a lot more, well, in the shape of a square, obviously. We have this box size that we can change in X, Y, and Z individually. So let's say maybe we do this like 900. And up and down, they have a lot of room to move, but side to side, not so much. And that really helps you creating certain shapes for your particle system. Like at this point, this kind of looks like a cone, and there's a lot more like going on in the center here compared to the top and the bottom. So that can create interesting looking shapes. And then if we add in the particle update something that makes it look a little bit more interesting even, like a vortex force will often do that. And we set the origin pull amount to something higher. I don't think we've talked about vortex forces before. Let's talk about it a little bit. A vortex force is a force that adds rotational movement to your particles. It does both rotational movement, but also pushes it away from the origin point. The origin pull amount is the amount that it gets pulled back. So if we set this to a high number, it will prevent the particles from going out as far, and if we set it to a really high number, it'll actually start sucking particles back in, like at 500 something, right? We can see that it starts sucking particles back in, and now we have a really neat little effect where any particles that get shot out too far anyway, they just kind of get killed. And with the next video, we're going to be talking about particle events. We can actually make some use of that, and that can be really, really quite cool. Now, if we change this from spawn burst instantaneous, by the way, to a spawn rate instead, that will probably be a little bit better for an effect like this. So let's say that we are spawning 150 units per second instead. And now you can kind of get to see how this works. It's quite nice, quite fun. Next time, let's build upon this with particle events. One of the most important ones is particle death. You can do things whenever a particle dies, and that is really, really exciting. But for now, we're going to keep it to this relatively straightforward. Next time, there's a lot of things to talk about, because particle events are probably one of the most awesome and exciting things to make your particle systems look very fancy fairly easily. Last time when we left off, we made this where we kill particles when they go outside a certain box-sized shape, which is quite fun and quite nice. Now, today, we're going to take that to the next level, and we're going to use that death information for some new stuff. We've been working in effectively only emitters up until this point, because for the most part, that's going to be where you spend your time, is making emitters that look good, and then eventually combining them together. But what we're going to be doing today is only possible inside of a system, because you're going to be linking one emitter to another based on events. So let's make a system. We have this death emitter. Let's make a system out of that. And we can, if we just real quick apply the changes here, the system will reflect that. We now have this system that has like this infinitely spawning like vortex of particles, which is quite nice. A lot of particles are also dying. So let's do something with that, right? I want to add a emitter here, and we're going to be adding, it doesn't actually matter what we add, to be honest with you. So let's just add an empty emitter. We're going to be setting up our own particles for this. We don't need to put in an emitter update to spawn particles. The only thing that we really need to do for that is just, we can spawn particles real quick, just to see what the particles look like when we spawn them in. Because they are going to be looking like this, which is maybe not exactly what we want. So just for the sake of showing things happening, when the particle spawns, we're going to set the color, which actually we can just do an initialize particle, now that I think about it. So particle color, we set to just like a bright red. And maybe we set the particle size to something a little bit lower. Maybe random uniform would be better. That would probably be a good particle size. So now we can get rid of the spawn rate, because we're not going to be spawning them in emitter update. We're going to be spawning them based on an event. And that event is when a particle in this emitter dies. So let's add that. In our particle update here, we can generate some events, either collision, death, or location events. We're going to be talking about death events first, because that's how we started this video, how we left off last time. I'm also going to show you some collision and some location events and how you can use those. For now, let's just go for a death event. So whenever something dies, it's going to be sending out an event. Now, you do want to make sure that the death event happens after you kill the particles, otherwise it's going to check for the particles that have died in this update loop, see nothing has died, and move on, and then kill the particles. So you want to kill the particles and then have the death event check. You'll also note that your compilation fails. You won't be having any particles anymore. Just click on the node as a whole, and we're going to go over here to this little tick box here, requires persistent IDs. You want the IDs of every particle to be persistent, since now it actually matters which particle is which on every frame, because they're going to be sending out events. For death events, that only happens once when they die, but specifically for things like collision and especially location events, it's very important that the system can keep track of every individual particle consistently. Which also will mean that our sim target is limited to CPU sims. This is the other huge issue that I didn't actually talk about in the CPU GPU video, because I knew I was going to make this as a separate video, and that is GPU particles. Because they're just rendering pixels to your screen, they're not actually physically present in the world, there's no actual logic happening behind them, they cannot communicate with each other in this way. So if you want to set up particle events, which for a lot of like interactive and fun looking particle systems you will want some of that probably, you are limited to CPU only emitters, which is a little bit too bad. So let's set requires persistent ID to true, and our particles are back. So now on our new emitter that we have over here, we can set up a new stage for an event handler. So we need something to handle the events, to receive the events, to do something with them. So this event handler we can assign to an event, and it can be assigned to any event on any emitter in your system. In this case, we only have the one, that being the death event of our death particle emitter. So let's assign it to that. And we want to execute this on all the spawned particles. This will be relevant because if we set this to every particle, our event handler is going to also be working on any particle that we spawn in through the normal means, but we're not going to be doing that. If you do want that to be the case, I guess you can set it to every particle. Most of the time when you set up something like this, the second emitter is only ever going to be used to spawn in particles in a response to an event. So in that case, you want to set it to being spawned particles. Now, the maximum amount of events per frame is there to limit the amount of stuff that can happen in a single frame. If you have like 1,000 particles die in one frame, you maybe don't want to have 1,000 responses to that from this emitter. So if you set this to a maximum of like 15, every frame, even if 100,000 particles were to die, which you're not going to be simulating 100,000 particles because, again, we're limited to the CPU, only 15 of those will actually be picked up by this event. If you set this to 0, it's unlimited. Then we have the spawn number. That is the amount of particles that get spawned in response to the event. So for now, let's set this to like 15, which can be quite a lot. And we can already see that it's spawning in a particle right in the middle here. This particle over here, this red and orange one, is being spawned in response to all of those death events. But it's being spawned at the exact center because we're never specifying where it should be spawned. And for that, we can add in the event handler stage, we can receive a death event. And this will, as you imagine, spawn particles in at the location of the actual death event. So we've got the position here, we've got the velocity, we have the acceleration, the random number float, like all of the information from the particle that died is getting put through to the new particle. So if we set the velocity to being true, that's a very high number, let's maybe just say 2, this should then inherit the velocity with 2 times the speed. Of course, for that we do need a solve forces and velocity, but now anytime a particle dies, it's going to spawn 15 more particles that get shot out at twice the speed of the initial particle, which is a little much. Of course, then in particle spawn we can also add our own velocity on top of that. So instead of inheriting the velocity, maybe we don't want to actually do that, right? Again, they're just going to be sticking around, but now they're also moving upward a little bit because when they get spawned in, they still get their own velocity. So we can just set this to a random range vector. And let's set this to like 500. And now we can see it kind of, well, it's only spawning in this direction because they're spawning from 0 to 1. So right now, this is kind of just like exploding all over the place anytime a particle dies. Now, these are a lot of particles for a CPU, so probably don't fully do this. But let's keep with applying this, and then what we can do is, instead of just adding velocity like this. Now, with those two combined, of course, we have our receive velocity that is going to just put through at about 2 times the rate that the original particle was moving at. And then we can add a velocity to that, which we can, I just made a new one real quick just because. We can do a random vector in a certain scale as well. So if we set this to like 500 again, it's going to be, maybe 500 is too much. Let's set this to like 3 or 30. 30 is pretty good. So now, anytime we have a particle die, it spawns in 15 new particles that move in the general direction that that particle was moving, but then also get a little bit of randomness added to themselves, creating this kind of like firework particle kind of look. Now, I think that these do live for way too long, so let's set them to a lifetime of between like 0.5 and 0.12, maybe. And then also add in a little bit of drag to them. And now we're spawning in stuff in response to a particle death. Now, I did prepare something that goes like a couple of steps deeper than this, just to show you how ridiculous we can make this. And that is, I believe, this one, right? So what I'm doing here is I'm spawning in particles. The moment they reach this first sphere, they die. So I think this sphere is just like an emitter that emits one mesh. Then we have this particle events here, which has a kill particles in volume. Outside of a 100 unit big sphere, they die and spawn in a bunch of new particles, which also generate death events when they die, when they go outside of a sphere with a radius of 250, which then is picked up with this particle emitter, which does the exact same thing, except that it generates death events at 500 units, and so on and so forth. Now, your CPU doesn't like this. Don't do too much of this. This is just putting things to their absolute max just to show you that you can do this if you want to. But like putting 20 of these into your level is probably going to tank your frame rate because your CPU, again, does not like it. I'm just going to put this into the level real quick and you can immediately see my frame rate did not like that. Like, I'll show you, I'm at about 80 frames per second right now. If I just copy this over a handful of times, I can see every time I copy it over, my frame rate absolutely tanks. Then when the particles are done emitting, of course, there's no problem because there's no more particles. But if I now select all of these, and this might actually crash my engine, so I'm going to save everything, and I auto-activate all of them off and then all of them on, my frame rate is, just by emitting like 5 of those particle systems, dip to like 20 frames per second. And that's because it's all CPU bound and it's spawning in potentially like tens of thousands of particles, because what you need to understand is I also used the value 15 for this one, right? So initially my spawn burst here spawns in, let's see, I think it's like 100 particles. Then at this point, for every one of those 100 particles that dies, it spawns in another 15. Meaning that now we are working with 1500 particles, which is reasonable, that's workable. Then we multiply it by 15 again, meaning that we're in the neighborhood of like 22,000 particles at this point. Then we do that one last extra time. For every one of those 22,000 particles, we're spawning in another 15 when they die. Meaning that we're now up to in the neighborhood of 300,000 particles per system. CPU doesn't like that. I had 5 systems, which meant that we're probably simulating about 1.5 million particles there. Frankly, the fact that it didn't dip below 20 frames per second is a miracle. Anyway, those are the death events. Very fun to play with. I do want to show you the collision events as well. I'm not going to go as in depth about them because they work pretty much the exact same. So I have set up some collisions to begin with here. So we've got our particle, which is just a burst, and then we have on a collision event, so we have got generate collision event, which again, important to put that after the collision in the particle update. And then this thing just takes in that collision event, and we have a receive collision event, which just applies the position, and it gets in the collision normal. And it uses that, in this case, to be able to have the particles boost in the opposite direction of whatever surface they just hit. And now we've got a bunch of stuff. It's just a directional burst system that I used for this. And for this, the particles that it spawns in are blue. on every collision. So if we just, instead of doing this as spawn burst instantaneous, what I'm actually going to do is I'm going to set this as a spawn rate so that you can see it a little bit better. And we're going to be spawning like, I don't know, 50 particles per second. That seems pretty good. So you can see now, whenever one of these particles hits the ground, they just bounce around and they start producing other particles. There is one little issue that I didn't take into account here, and that is that this is now infinitely looping, and apparently we also need to set the responding emitter to infinitely looping, and now it will infinitely keep doing this. So we've now got like a raining effect that has like little splatters going on when it hit the ground, which combining this with a kill particle really is a decent way for a very localized version of having little rain droplets splatter around. Why do I say it's very localized? Because again, it's a CPU limited. You can't make a giant system with a lot, like thousands upon thousands of raindrops, all generate their own little things when they hit the ground, because it's going to kill your frame rate. But if you're making something that is cinematic and you're just rendering it, you can just do this because performance suddenly isn't that big of a deal anymore. Or if you know that it's going to be in a very specific small area and it's not going to be spawning too many particles, you can also get away with this. And this is a very accurate way of making sure that your like rain responses actually fit with whatever your rain particles themselves are doing, which is quite neat. And then the last one, I want to talk a little bit more about that, because that is this system here. You might be thinking, what even am I looking at? You are looking at position events. So much like a death event sends an event when a particle dies, and I should clarify, it only sends an event when a particle is actively killed. When it just reaches the end of its lifetime, there's no death event that gets set. It only does events when particles are explicitly killed. Collision events just send an event whenever a particle collides with something, if it has collision. A location event just sends through the location of your particle every single frame. So we have this generate location event, and here we can set the send rate. So if you set this to 0, again, it's just going to do it every single frame. If I set this to, for instance, 5, you can see it's a lot more choppy because it's only sending this 5 times per second. So this is kind of the frame rate of whatever your responding emitter is going to be doing. 30, for all intents and purposes, is well and good enough. Then the location event itself, of course, has the position and then a bunch of other stuff that it can just take into use if you want to, like the age of the particle, the velocity of the particle, whatever. For the sake of this system that I have over here, if I just add in a sprite renderer real quick, you can see that it's just adding a new sprites every single frame in the location that this system has its sprites in. So these sprites are moving in this way, right? Say, quite fun little way for the particles to be moving. This system is just adding particles every frame to the position of every particle in this. But since they're all individual emitters, if we do a ribbon renderer, they don't all get linked together. What happens is we get a ribbon that follows the path of every one of the particles in this emitter. If I just put in a ribbon renderer in here, it's going to be instead connecting all of the particles in this system, and that, or in this emitter rather, and that creates this weird ass drunk looking spider web. But instead, since every single particle in this emitter gets an emitter of its own, we can then start doing an effect like this, which is really quite useful. Again, I think I like the death and the collision ones more because they end up feeling more satisfying in a lot of ways, because usually you use that for kind of like a firework effect, right? When something dies, it explodes into more separate, smaller particles. When something bounces against a floor or a wall, it creates some sparks. Those are like the very fancy, satisfying things. I think location events are probably some of the more important ones instead. There's not particularly anything satisfying about being able to render a ribbon per particle in your emitter, but it is very useful to be able to do things like this. Now, we can also do slightly different stuff with this. We can also say, actually, I do want to have like a sprite renderer in this, and when I initialize the particle, I want to set the particle size to something uniform, something a little bit smaller than this. So maybe let's say like 5. And I want the velocity on startup, we then need to like fix extrude. I want the velocity to be this. And now we have like this happening where particles spawn in the location of wherever particles exist in this emitter, and they start going. And of course, I wouldn't be me if I wouldn't be adding some randomness to this. So let's add a random range float between 1 and 4. And now we get this, which already looks a lot more like visually interesting and intense, and there's a lot of stuff that you can do with this. So it's not only for just adding ribbons to particles, it's very useful for that, but you can also like create particles that kind of act as the origin point for an entirely separate emitter, and that creates a system like this. So now we're starting to work with how particle emitters can really work together aside from just existing in the same system to make something that individual emitters just simply couldn't do. Now, with all that, I think we are kind of at the end of this particle series. We could go on for a lot longer. I could show you, oh, and this is a fun thing that I once did, and this is a fun thing that you can do. But at some point, I think we've now covered the most important basics, and you can just start playing with things, discovering things one step at a time. And with this basic knowledge, it is now actually useful to go up on YouTube and look up specific like feature tutorials, meaning specifically, I want to make this thing, and watch somebody make that thing, and you'll actually understand what is going on a little bit more. So I think that is, for now, the most logical next step to do to get better at particles for you is to just go ahead and make some stuff. Then at some point in the future, I'll probably get around to making an intermediate particle course, in which we'll probably talk a little bit more about making your own modules and scripts. But for now, don't worry about that. Just go out and learn. I think to round off this introductory particle course, let's put all of our knowledge that we've learned together and make this particle system that we have here. A particle system that is just like a laser with some impact particles going on. And the most wonderful thing about it is that it has this little widget that we can move around to change the endpoint. And the little laser here will stay like consistent in its amount of detail as the laser gets longer, and the particles here always spew towards the direction of the laser, which is quite nice. So this will work fairly nicely as like an impact on the floor, for instance. Now they are all spewing upward. Let's make this to put all our knowledge together and really put to the test how much we've learned throughout this course. And the way we're going to go about doing that is I'm just going to make this as one big system. You can make these as separate emitters if you want to. There's also the fact that when you have a system, I don't think we've talked about this yet, but when you have a system and you've changed the emitter in it for whatever reason, you can right click, you can create an asset from this emitter. So you can just make your system, and if you don't want to reuse an emitter from that system, you can still make an asset out of it to reuse in other systems. So let's just start by making a Niagara system. It's going to be an empty system, and we'll call this our laser impact. Let's do the actual laser bit first. So emitter update, what we're going to be doing is we'll spawn burst instantaneous, and we're going to set up a beam emitter setup. For the time being, let's set the spawn count to something like 10. We're going to set this more programmatically in a moment. But first, I just want to add in all of the little modules here so that we have what we're going to be working with, and then we can start tweaking things a little bit. Particle spawn, of course, we have our initialize particle. Then I also want to spawn a beam, because we're going to be using the beam setup for this. Then in particle updates, we have our standard particle state, but I also want to jitter the position of the particle, which we've talked about. We'll do this, create like a noise offset for its position, And then let's also just set the color in here. I guess we can do it on spawn as well if we prefer. And instead of doing a sprite renderer, what we're going to be doing is we're going to be doing a ribbon renderer, of course. And that looks like this now, which is not exactly what we're looking for, right? So with all the modules created now, let's actually start filling them out. First and foremost, in our initialized particle, we're going to set this to 1/4 of a second lifetime, which will be a little bit better for us. And then in the system, what we'll do is we'll set the loop duration to the same amount so that we can more easily preview it. Now we can see it creates them over and over and over and over again, giving us a slightly more like real world look at how this is going to behave in our levels. Now, for the amount of particles that we're going to be spawning, I've set this to 10 at the moment. We're going to actually set this as a user parameter instead. So that's just going to be a common, which can be a float. I suppose it could even be an integer, to be honest with you, because it's going to be a whole number anyway. So let's do an integer. And this will be our spawn count. And by default, set that to something like 25. And that's going to be dragged on top of our spawn count here. That way we can set the actual spawn count on runtime in the actor that we're going to be making for this, because we're going to be making a specific actor with a little bit of extra code to make this work as well in a moment. And then while we're at it, making user parameters, we'll also make a new common vector user parameter, and this will be the end position. So by default, let's set that to like 200, 0, and we're going to be using that to set up our beam. So in the beam emitter setup here, and for the beam start here, we're going to just stick with simulation position for now. The beam end, of course, will be our end position that we just made. If you want to make something that, for whatever reason, can have a offset starting position as well, there's a little bit more math involved in all that. We're not going to go into that right at the moment, but that is possible. I'm just like referencing the thing that I made to prepare for this. And here what we're doing is we change the beam start to a add vector, convert position to vector, and then the input position will be the position of the particle system, and we're adding to that a starting offset value as well. Entirely possible. Again, that was just me messing about a little bit. For the most part, entirely unnecessary as well. Now let's go into our initialized particle right here, and I want to set my ribbon width to direct set, and we're going to set that to a thicker value. Now let's actually set up the color real quick here. So what we're going to be doing is I'll actually make a parameter for that as well. Let's make a linear color here, and that'll just be the color. Let's set the default value to like red or something like that, orangish. That's going to be our default value, but I actually want to multiply linear color by a float for the intensity. So we'll get our color here, put that in there, and then also add in a new float for the glow intensity. And let's set that to like 10 by default. And that's going to go in there. So now that color is going to get multiplied by the float, and because it's emissive, we get this. Maybe even like 20 as a default value. Maybe even like 50, honestly. Like, don't be afraid to make this quite a high value. Still doesn't look particularly great though. And that is because the jitter position is kind of off. First and foremost, the jitter amount needs to be way, way less. But also, we need it to be only jittering in the middle, not on the ends. We don't want the start and the end of this ribbon to actually jitter about too much. We've done this in a previous video, I believe, so I'm going to go over it pretty quickly, but we can get a jitter amount from curve, and instead of using the normalized age, what we'll do is we'll use the link order. So if we use the ribbon link order, we put in a curve that looks a little bit something like this, you can see it's only jittering in the center. Of course, what we'll actually want to do is we'll want to move this one as far to the left as is reasonable. We'll make a new key, which you can do by using the middle mouse click button. The key data is going to have a value of 1 in the second slot there, and then we'll pull that across as well. And now we can see over here, the entire thing is jittering except the beginning and the end. And now we can slowly start to scale up the amount of jitter. And maybe the spawn count's also just a little on the high side, to be honest with you. There's a little bit of experimentation needed here for getting good values. as is usually the case. Or maybe we want to actually have a slightly higher amount of particles which jitter less. That actually probably looks a bit better. And maybe we even want this one to be like closer to both of the ends, which you can just kind of mess about a little bit. Get this back to 1. This looks pretty good at this point, I would say. So now, if I change this end position to something like 100 units to the top, it starts going in that direction and so on and so forth. So we have a very easily editable like lightning strike at the moment. Now, for the next one, we're going to be adding another emitter, and we're going to be using the fountain as a base, just because it is kind of the easiest way to do this. So we start with this, which obviously doesn't look very good. We'll stick with the spawn rate of about 90 for now. I think that's pretty good. But we won't go into the shape location here, because the shape location we don't actually need. We'll delete that. We're going to be setting the spawn location for this in the initialized particle instead. As you can see, we can use the position mode, which is where the particle spawns to begin with. I'm cutting in real quick here during editing. In the setting position directly, you actually want to set this as simulation position, not as direct set. And then we use the offset mode for the end position. If you see anything else later in the tutorial, when we go back to initialize particle, ignore that. I kind of just selected the wrong thing. So I'm recording this after the fact to fix that. Now, for the velocity, it's just spewing upward at the moment, which is obviously maybe not great. What we want to do is we want to calculate the direction between the end position and the start position, because that is what the cone axis needs to be in our add velocity. So for this, we will get a subtract vector, and we're going to be subtracting the end position from the starting position. So we can drag in the end position here, and that will then be spewing towards 0, 0, 0 now. So no matter where we are, again, if we have this like very high up, you can see it is now spewing toward there. If we set this to like all the way over there, or maybe even in the negative, the other way around, it's always going toward the origin point. Of course, if you're using a start position value as well, you then put that up in the A slot for subtract vector here. Let's set these back to some decent default values. And that honestly is the hardest bit that we are going to work. And then in our particle update, we have a scale color here. We're actually just going to copy over the scale color from this one because we'll delete the one that exists so that they have matching colors. You can add a alpha fade out for these as well. What I personally prefer to do for these kind of like spark type particle effects is I just scale the size instead. So scale the sprite size, and we just kind of scale those down linearly into nothingness. That just feels a little bit more like they're emitting sparks. For the gravity force, that's entirely up to you. I like making it a little less strong for these ones, so going down to like -500 maybe. So that there still is some gravity, but just not as much. And the same thing you can say with the velocity here. It's between 500 and 850. Maybe you want to set that to between like 300 and 900 instead. So there's a little bit more variance in there. Makes it feel a little bit more erratic, a little bit more like actual sparks flying all over the place. I think what's more important though is in initialized particles, setting the lifetime to something more reasonable, like a quarter of a second to, let's say, 0.4 seconds. So they don't live as long, and suddenly that already looks a lot better, doesn't it? So actually set the end position to like 200 so that the laser is a little bit longer. And if you want to, you could increase the drag a little bit as well, so that they slow down a little bit more. Again, as they start to slow down and lose mass, is kind of what you're implying there. The drag probably would slow them down a little bit as well. Now, the most important thing to make this look better, to imply that they're like sparks, because right now they're just a bunch of circles, right? So if we go back into initialized particle real quick, we can see the sprite size mode is set to random uniform. We're going to be setting that to random non-uniform, meaning that they will be all sorts of shapes and sizes, and already you feel like this looks a lot better. So I'm going to set the minimum sprite size to like 1 and 1, and then the maximum to like 7 and 7 or something like that, which makes them so much more varied already. Maybe we can experiment with like 2 to like 9 or something like that. And the last finishing touch that really makes this work is going into the sprite renderer and saying the alignment, instead of automatic, we're going to be aligning them to their velocity. So now they always will align themselves in their rotation to their velocity. So they seem to like actually be moving around in the world and keeping their rotation and shape based on like that they're being given due to the non-uniformity of their scale. And that is effectively the particle system. So now let's make an actor to put this particle system in to start driving some of these things, and we can actually put them into the world with that. So we make a blueprint class, just a normal actor. This will be our laser actor. And in there, we will add in a Niagara particle system component, which we'll just keep as Niagara. And we'll put in our laser impact here. And you can see we have all of our parameters that we had before are now exposed in here as well. So we can set the color to something different if we wanted to. And there we go. We're going to be influencing this in the construction script. We'll get in our Niagara particle components, and we will set the vector parameter for the end position. And we'll make a variable for that in a moment. And then we'll also set a integer parameter that we had made. And actually, let's see, I called it end pos, so for end position. So we actually want to copy that name over exactly, because it's important that these names match exactly. And the same thing here for spawn count. We're going to copy the display name, and we'll paste that in here as the parameter that we want to be setting. Now, we have a variable tab here. Let's make a variable for the end position. And that will, of course, then be a vector. We can just plug that into the vector end position. That's as easy as that. We'll set the default value for it to the same, so 200, 0, 0. But now we actually want this vector to also drive the spawn count. Because the issue that we have right at this moment is if we like compile this, that's very, very nice. If we make this very long, we still have the same spawn count, and we kind of lose all of the detail that we had in our laser. And if we make it very like squashed down, all of those spawn counts are going to like do this, which also doesn't look that good. So the longer our length is here, the higher our spawn counts need to be as well. And that is easy to set up, because the easiest way to do that is we can just get our vector, get the vector length out of that. And then you can divide that by a number to make it more reasonable. In my case, I used 3. And that will then go into here, which will be truncated, meaning that it's only going to be using everything before the decimal, and that will set the spawn count. And as easily as that, now if we go into the end position and we do set this to like 20,000, we still have all of that detail all the way across, because it's now spawning in a frankly ridiculous amount of particles. And that is pretty much all there is to it. Now, the only thing we have to do is in the end position variable, we'll actually make sure that the typo is fixed there. We want to expose that, make that public. But then when we've made that public, we can also show 3D widgets for a vector and things like transform variables. You can show 3D widgets, which are useful if you're using a vector specifically for a position offset kind of thing. Because now if we drag that into the level, you can see we have this widget here and it will update like that. Now, one last thing that I want to talk about is the fact that you probably like want to collapse this into a function real quick. So we can say collapse into function update laser particle, because now we can also use this in our event graph if we wanted to like on begin play, like do a timeline or something like that, right? Which then updates the position. You can animate this through code that way, and you can just reuse this update laser particle function however you want. We're not going to be doing that because, again, this is a particle video. This is a particle tutorial course, not a coding course. So you can figure that out on your own, or like watch my other tutorials to learn more about that as you go along. And now we have the particle system from the beginning of the video, more or less, right? Wherever we put this end position is where this laser is going to be aiming. The impact particles, the little sparks, will always follow accordingly as well. So that's been the entire particle introductory course. Again, there could be an entire like future course going over the more intermediate stuff instead of setting everything up in these module details panels. For some things, you just kind of maybe want to make your own modules. We can dive into that in a follow-up series. For now, I think you've gotten the tools out of this series to Start playing about with particle systems, start experimenting, start making some fun little things, and maybe in the future we can expand on that a little bit more. And a very big thank you to all of my Patreons. You can see them on screen right now. If you want to help out supporting the channel, there's a link down below in the description to the Patreon page. A huge thank you to my Cave Student tier supporters, Earl Monseval Erno, and my Cave Digger tier supporters, Sir J. Thomas,